Very good afternoon and welcome to the Energy Technology Perspectives 2016 webinar. My name is Daniele Poponi. I'm the project manager of the Energy Technology Perspectives 2016 project, and I will be moderating the webinar. The webinar will take a deep dive into the topic of the ETP 2016 report, namely sustainable urban energy systems and how low-carbon technology deployment and sustainable energy strategies in cities can lead to urban decarbonization, and also how cities can contribute to national and global low-carbon transitions. Before we start, I would like to welcome Jean-François Gagné, the head of the Energy Technology Policy Division, to give introductory remarks and introduce you to the webinar. Jean-François, the floor is yours. Thank you.
Thank you very much, Daniele, and welcome to the webinar, everyone. I see that we have quite a high attendance again this year. This is very encouraging for us. This is a very large project that the IEA has been doing for 10 years now, so today's edition is very special for us because it marks our 10th anniversary of the IEA doing analysis to try to demonstrate the role that energy technologies can play in meeting multiple energy policy objectives. And so we're very happy to see the high turnout. We hope that everybody's going to get a lot out of today's discussion and that this will be the beginning of further discussions between the IEA and you in the future. As I said, this is a very special edition, both because it is our 10th anniversary, but also because it is the first Energy Technology Perspectives that we release under the authority of our new executive director, Dr. Fatih Birol, who came to the IEA as executive director in September last year, and also it is the first one that we published under the new strategy of the IEA, modernization of the IEA, which basically is bound in 3 pillars. Increasing the IEA's work in terms of energy security, which was the IEA's original raison d'etre or mandate, but also opening the doors of the IEA to all global energy stakeholders, as well as a very strong focus on clean energy and energy efficiency, and in our case, today's case, which is very important, on clean energy technologies. So you can see that there is a lot of excitement at the IEA about this new strategy, especially in a year like 2015, which we think was probably a pivotal year in terms of being able to change and transform our energy system towards a more sustainable future. In fact, if you look at a little bit at the context in which we are publishing this book, we're coming out of a year that had quite a few major outcomes. The first one being that for the first clear signs of decoupling between CO2 emissions and economic growth have started to be confirmed. So this year, or the year 2015, saw global energy-related CO2 emissions remaining flat for a second year in a row, while the economy still grew. This is the first time in history that we have had flattening of CO2 emissions with economic growth. We only had 3 other episodes of CO2 flattening, but those were associated with an economic recession. And so we are starting to see this, what we call the happy divorce of economic growth and energy-related CO2 emissions, and we're very hopeful that this is the beginning of a new trend. We also saw at the same time a huge push by many governments to enhance the role of clean energy technologies in terms of overall energy supply, with, for example, last year, renewable power capacity going at record high installations for the second year in a row, with over 150 gigawatts of installed capacity. And so that's more on the fact or the results of different actions, but we also saw 2015 as a major milestone in terms of the resolve and the importance that policymakers is putting towards sustainable transformation. COP21 was a historic push for clean energy with, I guess, 2 major aspects. The first one is looking at collaboration as the basis for an agreement on climate change mitigation. We moved from a top-down regulated approach to a country-based constructive approach with more than 185 NDCs being brought forward to demonstrate what countries will be doing to change the way they've been growing energy and their economy in the past. There's also been an enhanced ambition with new goals put forward with the aim of going well below 2 degrees with a possibility of achieving 1.5 degrees. And this is going beyond even what was an originally conceived difficult task when we started this study 10 years ago, and we're very happy to be able to work towards demonstrating that that clean energy transition is not only feasible, but it's also economically sustainable. And then finally, a major outcome of the COP was the great recognition that innovation and technology are essential pillars to be able to meet our ambitious climate goals. And again, for us at the IEA, this was a major support to continue doing our program of work. And we're very happy that we launched this year's Energy Technology Perspectives 2 days ago at the Clean Energy Ministerial, which was a joint meeting of both the Clean Energy Ministerial but also the Mission Innovation Ministers, who announced that they would be doubling their R&D investments to support a sustainable transformation. So we do believe that there is a wind of change happening. We certainly hope that ETP can be one of the pillars in terms of moving towards an implementation phase now leading into COP22, and we're happy that we're going to be part of that overall work. And I think this year's focus of ETP on sustainable urban energy systems demonstrates our willingness to support that implementation by focusing at where action needs to be taken. I mentioned that the IEA now has an open door policy, wanting to work way beyond our traditional IEA membership to make sure that emerging economies, where most of the action will need to take place, are an inherent part of our discussions and our analysis. But we also feel, coming out of COP21, really was working on a new modus operandi of having non-state actors participate in the debates and in the run-up to the agreement with an increased participation, for example, from the business community, from non-government organizations, as well as local governments, as well as actions like the Paris Pledge call for action to support the increased ambition and the tracking of progress. We think all of this bringing different actors together was very important. And so you'll be hearing today in this presentation how we see local governments playing a huge role in terms of meeting national policy objectives, and how national governments need to work with their local counterparts to ensure that the solutions that will be rolled into cities are solutions that meet both cities' needs and local governments' policy objectives, but also help us move towards our national and global energy policy objectives. So with those few comments, I want to again thank you very much for your very, very welcome participation. I think we have more than 150 people listening in to this webinar today. This is very encouraging for us. We hope that the information we will be presenting today will be useful in itself, but will also entice you to communicate with us again and want to learn a little bit more about our work, as well as visit our website where we have a lot of that information. And I hope that everybody will find today's discussions very, very useful. So with that, I want to thank Daniele for managing the project and being able to deliver on what I think is stellar analysis, as well as the entire team that you'll be listening in today. And I hope that you will enjoy our webinar. Daniele, thank you very much, and over to you.
Thank you very much, Jean-Francois. So now moving to housekeeping, the webinar will be structured into 7 presentations covering each ETP 2016 chapters from lead authors. Each presentation will last approximately 15 to 20 minutes, and if time allows, we'll take 1 or 2 questions at the end of each presentation, but we will have a longer Q&A session at the end. We obviously welcome feedback from attendees, and we will address questions also during the webinar through the Q&A online platform. So before we start, we would like to express our gratitude to the 200 plus contributors and reviewers. We embarked on the ETP 2016 project 2 years ago, and we felt it was a great learning experience, and the outcome greatly benefited from contributions provided by many colleagues inside and outside the IEA, which gave us the most valuable feedback. On a logistical note, we are updating our ETP contact list, and to which we usually send updates on our work and invitations to the webinar. We will show an email contact at the end of today's presentation, and which will also be available online in a few days. So just a few words on our ETP report per se, which is divided in two parts. The first part looks at the global energy outlook in the frame of the ETP scenarios, and also looks at the progress in clean energy technologies, and which is usually also a standalone report called Tracking Clean Energy Progress, which was presented at the 7th Clean Energy Ministerial meeting yesterday. And then part 2 of the report focuses on a specific aspect of the sustainable energy transition and includes a country analysis in one partner country. So with that said, I think JF described the thematic focus of ETP 2016 with great clarity, and so I would first introduce you to our first presentation on the global outlook. Our first speaker is Uwe Remme, which is an energy analyst in the ETP team, and where he leads the energy supply side modeling and is coordinating the ETP scenario analysis. That said, Uwe, the floor is yours. Thank you.
Energy systems. I would like to give you an overview about the global trends that we see in our technology scenarios. And so to start with, I just want to mention that we look in ETP typically at, also in the past editions, at 4 scenarios. So one is the 6-degree scenario. You see here the evolution of the global CO2 emission, that scenario in the upper line. And the 6-degree scenario, or short 60S, is a scenario where we don't impose any additional or assume any additional policy efforts to reduce greenhouse gases. So it's largely based on current trends that we see and could lead in the long term to temperature increase of around 5.5 degrees. Then we have what you don't really see in the graph here, but we also looked at a so-called 4-degree scenario, or 4DS, and that aims to limit the temperature increase in the long term to below 4 degrees, and assumes, in addition to the current policies, also policies that are currently under discussion or planned or pledges that have been made by different countries. And finally, the core scenario of ETP is a so-called 2-degree scenario, short 2DS, which, as the name suggests, aims to limit the long-term temperature increase to below 2 degrees. Okay, how do we get from the 6-degree line that you see at the top to the emission trajectory that we aim for in the 2-degree scenario? On the technology side, important part is end-use energy efficiency, contributing almost 40% of the cumulative CO2 reductions to get from the 6DS to the 2DS. If we add also fuel switching in the end-use sector, so meaning switching from carbon fuels, for example, to electricity in the end-use sectors, almost 50% of the cumulative reductions are achieved by these 2 measures. The additional reductions are then achieved by renewables in the end-use sectors, but also, for example, in power generation, contributing around 1/3 of the cumulative reductions. Then there's also a small contribution to improvements in fossil fuel power generation, but overall the share of fossil fuel power generation declines, as we also see later in the presentation, so the contribution is rather small with 1%. and CCS and nuclear account for around 12 or 7% of the Q limit reductions. How do these different technology options, how are they used in the different sectors? That's shown in the graph that you see at the bottom. So if we start with renewables, you see that large contributions of the reductions are achieved by renewables in the power sector, but also in transport, talking then about the use of biofuels for long-distance transport modes. If we look at CCS, it's particularly important in power generation, but also in industry. If we talk there about the reduction of process-related emissions, so that are emissions that are not related to the use of energy that much per se, but rather to the production process to produce materials, but also in the transformation sector. So there, for example, CCS is used in the production of biofuels. If we move on to the next measure, which is fuel switching, so that's switching to lower carbon fuels, as I said, for example, fossil fuels to electricity. So it's particularly important, again, in the transport sector, where we switch there to electric vehicles, but also in other sectors like buildings and transport. Then energy efficiency, I already mentioned, that's really a huge opportunity for emission reductions, and there we see huge reductions in cumulative emissions in all the three end-use sectors and also in fuel transformation. And finally, nuclear, that's apparently also contributing to CO2 reductions in the power sector. Overall, we can conclude the long-term strategy based on a portfolio approach is needed, so it's not just one technology or technology area that can provide these emissions reductions, but really we have to look at the entire portfolio of technologies to reach the very ambitious reduction target to limit temperature increase to below 2 degrees. If we look at the energy mix, so what's shown in this graph is the global primary energy demand. And if you look at the situation today, there 80% of the primary energy use is based on fossil fuels, meaning coal, oil, and gas. If we move on to our 6-degree scenario situation in 2050, doesn't really change that much. It's still around 79% of the primary energy use is based on fossil fuels. But we see then a drastic change or some change already if we go to the 4-degree scenario. So there the share of fossil energy carriers reduces to 70%. And then if we look at our 2-degree scenario, there we see a drastic reduction in the use of oil and coal in the 2-degree scenario, and the use of gas is slightly below today's levels or the level that we saw in 2013. On the other hand, we see that biomass becomes the largest primary energy carrier with a share of around 1/3, and overall the share of fossil energy carriers in the 2-degree scenario falls from 80% today to around 45% by 2050. So highlighting the important role that we see of low carbon energy carriers like bioenergy, and at the same time it means also that in 2-degree scenario we are not stopping, at least by 2050, not stopping using fossil fuels. They're still an important part of the energy system. If you look at the different sectors, so again you see here the emission in the 6-degree and 2-degree scenarios, again on a global level. So what's the contribution of the different energy sectors going from the 6DS to the 2-degree scenarios? So all three end-use sectors, so buildings, transport, and industry, combined together are in the position to kind of stabilize the CO2 emissions level that we have today. And then additional reductions are achieved by decarbonizing power generation, so that's 40% of the cumulative reductions, and also some contributions in other sectors, like agriculture and also fuel transformation with around 6%. So what becomes apparent from this graph really is that all sectors needed to achieve the 2-degree pathway. In the following, I just want to give a brief overview about the actions needed in the different sectors. I would like to start with the power sector. And what you see here is the evolution of the electricity generation mix in that scenario. Today, power generation is responsible for around 40% of the CO2 emissions, including also process-related CO2. And if you look at the evolution over time, the remaining electricity demand in the 2DS is almost completely decarbonized by 2050. falling from 530 grams per kilowatt hour today to less than 40 grams per kilowatt hour in 2050. Or we can also look at it differently, that if you look today at the share of fossil fuels in generation mix, that's around 70%, while renewables account for around 22%, mean by 2050 we see a kind of reversal of these shares. So renewables account for 2/3 of the generation mix, and fossil fuels, including CCS, are responsible for just 17%. So here we see a kind of drastic change in the generation mix in the 2-degree scenario, but it also provides, to achieve these drastic transformation requires quite some challenges. First thing we have to note is really the increased deployment of low-carbon technologies. For example, on average, 118 gigawatts of solar capacity have to be added each year between 2050 and 2050, which is more doubling than the rate that we saw in the last year in 2050 of around, preliminary numbers indicate that around 45 to 50 gigawatts of solar PV has been added globally. Second aspect to keep in mind is also that we not only have to talk about the deployment of low-carbon technology, but also have to look at the existing fossil-based generation. So even today we've got a capacity of around 1,200 gigawatt of coal capacity that can still operate in 2050 and could emit of around 5.4 gigatons of CO2 in 2050. That's way beyond the CO2 emissions that we envision for the power sector in the 2-degree scenario of around 1.4 gigatons. So clearly, for the existing fossil-based generation stock, one also has to look at issues like early retirement of plants, retrofitting of existing coal plants with CCS, or also co-firing with biomass to reduce these carbon impacts of the existing coal fleet. Finally, as you see from the increasing share of renewables in the 2-degree scenario, also the question of integrating increasing share of variable renewables, mainly solar PV and wind, into the electricity system becomes a challenge. So in 2050, the share of these variable generation sources increases from 3% today to 30% by 2050, and there one has to look at opportunities to increase the flexibility of the electricity system. So options there are a more flexible generation, for example, gas-fired generation. One has to look at storage options, electricity storage, but also thermal storage if one thinks about the linkage between electricity and heat. One demand response is an option, for example, flexible charging of electric vehicles, or interconnections between regions to increase the balancing area and just that way reduce the variability of renewables. Overall, these options are available, and their deployment really also depends then on the local conditions and opportunities. So that much to the power sector. The following, I just want to look at briefly at the building sector. The building sector today for or consumes around 125 exajoules, or 30% of the global final energy demand. And the residential sector is a major consumer, around 75%, and the remaining 25% are due to the commercial or so-called services sector. If you look at the figure, what you see there is the strong differences of variation between the use of these use of energy for different energy services or energy services in the building sector. So, for example, in the OECD, you see that around 50% of the energy is used for space heating, while in non-OECD countries we see that 60% is used for water heating and cooking also then including the traditional use of biomass. And as mentioned before, buildings account for around 30% of the global final energy demand. But surprisingly, it's only, first look surprisingly, they only account for 8% of the direct CO2 emission. And that's largely due to the fact that 60% of the energy used in buildings is either based on electricity, district heating, or renewables like biomass. And with electricity having the largest share of around 30% today. So if we include these upstream emissions, for example, like electricity, into the emission balance of the building sector is today responsible for around one third of the global CO2 emissions. how does the situation in the building sector evolve in the future? So what you see here is the global final energy demand in the building sector in 2050 for our 3 scenarios. The driver for the building sector, especially the growth in building floor area, also population, but building floor area is expected to increase by around 85% in non-OECD countries. That's really the driver for the energy consumption. To more modern fuels, from biomass to modern fuels, with increasing income and also increased access to electricity in developing countries. If we look at the 2-degree scenario, we see that effective action to improve building energy efficiency could limit the building final energy demand growth to just 5% above current levels in 2013 without changing comfort levels, meaning the end-use service demands being provided. Coal and oil use in the building sector decreases by around 3/3 under the 2-degree scenarios, while natural gas consumption falls by around 50%. And as a result of all these trends, so increased energy efficiency, but also switching to lower carbon fuel or renewable in the sector, the 2DS can lead to a 40% reduction in annual direct emissions in 2050 compared to 2013. So that's has been a brief overview of the building sector. Following, I just want to talk briefly about industry. So today, the industry sector is responsible for around 40% of the final energy demand. As you see here in the graph, it's the evolution over recent years. So it's around 150 exajoules have been used in the industry sector in 2013, and around 70% of industrial energy use is used in so-called energy-intensive sectors. So we're talking there about chemicals and petrochemicals, cement, iron and steel, aluminium, and also pulp and paper production. If you look at what's shown in the graph, the kind of regional distribution of the industrial energy use, we see that in OECD countries, the industrial energy use has been stagnating around 30% of global final energy use in industry, while the growth is driven by non-OECD countries, mainly China dominating today with around 1/3 of industrial energy use. But over the next decade, we also expect demand growth in other parts of other emerging and developing countries. If we look at the industry sector in our scenario, so what's shown here is on the left side the CO2 emissions, and on the right side you see the final energy consumption. The upper rim of this red graph shows 60S, and the lower rim is the 2-degree scenario. And there we see that in the 60S we still see an increase in CO2 emissions in the industry sector, accompanied also by an increase in final energy use. In the 2DS global industrial direct CO2 emissions peak by around 2020 and decouple from industrial production growth. And by 2050 we see that the CO2 emissions in the 2DS could almost be halved or 50% below the 60S level. The sectors that have the largest emissions reductions in the 2DS are iron and steel with around 1/3, followed by chemicals and petrochemicals with around 1/5, and still around 13% is provided by cement. And the main options, technology options to reduce emissions in the industry sector are energy efficiency, which provides more than 50% of the reductions. That corresponds to the reduction in final energy demand that you see in the right graph, followed by the introduction of innovative or new technologies. So there, for example, particularly as mentioned before, process-related emissions. The basic solution there today that we expect in the 2-degree is largely CCS, which accounts then in total for around one quarter of the cumulative CO2 reductions. And the options are switching to lower carbon fuels, being biofuels in industry, and also increased recycling, for example, in iron and steel, aluminium, or the paper sector. And on the policy side, 2DS requires kind of cross-sectoral and public-private collaboration, and one also has to look at international policy action to get R&D and also access to technology transfer on track, and also to provide incentives or improve incentives for energy efficiency and reduced emissions. The last sector I would like to talk about is the transport sector. The transport sector today accounts for about 1/4 of global final energy demand and 1/5 of global energy-related CO2 emissions. The fuel mix is dominated, as you see here, the purple area, that's oil product, is clearly dominated by fossil fuels, by oil today, with a share of around 95%. And if we look at the 2-degree scenario, the transport energy demand will need to peak before 2030 and reach by 2050 a level 50% below the level that we have today. So broadly, the transport energy demand stays around 100 exajoules in the 2-degree scenario. This is realized through a mixture of strategies and instruments that can be summarized under the keywords avoid, shift, and improve. Avoid means avoiding unnecessary transport demand. Shift means to move to transport demands which are less energy intensive, to shift transport modes that are less energy intensive. For example, we're talking there about shifts from aviation to rail and passenger transport. And the third action is improve, or the third keyword is improve, meaning talking about improved vehicle technologies. That means, on the one hand, improving the existing or a conventional drivetrain in vehicles, but we also talk about introduction of new technologies like electric vehicles or the introduction of biofuels in some transport modes. And the latter factor, the improved strategy, becomes apparent if we look at the fuel mix. So in the 2DS by 2050, the share of oil drops to 60%. As I said before, today it's around 95%, followed by biofuels with a share of around 25%. Electricity accounts for 10%, and the rest is split among or is covered by hydrogen and natural gas. If we look at the CO2 emissions in the transport sector, so you see here that graph illustrating the contributions of the 3 strategies that I mentioned: avoid, shift, and improve. And in the 2DS, transport emissions will need to peak and begin to decline within the next decade, and that will require considerably faster improvement that we see in terms of decarbonization than historic rates. Greenhouse gas emissions from transport in 2050 will need to be reduced by almost 1/3 relative to the levels that we see in 2013, and the contribution, as you see also in the graph, from the 3 strategies, avoid, shift, and improve, is roughly each of them contributes around 1/3 of the cumulative emission reductions. But the trends or emission trends that we see in different parts of the world, here differentiated in OECD and non-OECD, differs. So if we look at the OECD, transport emissions have basically stabilized, but a significant reduction is still needed in the 2DS. If we look at non-OECD economies, their transport greenhouse gas emissions are on track to overtake OECD in the next 5 years. The challenge there will be, in the emerging economies, will be to avoid, due to the strong transport demand, that they follow similar development trends that we've seen in the past in OECD countries. So that way, the kind of strategy for non-OECD economies really has to look at different ways to cover increasing transport demands in the future. With that said, I will conclude my presentation, or the overview of the global trends in our scenarios, and hand back to Daniela.
Thank you very much, Uwe. We do have time for at least 2 questions from the audience. So the first one, you mentioned challenges what do you consider the most important one?
I guess the challenges, I mean, it really depends on the sectors, as you've seen in the overview of the sectors. But a kind of common element is that we, on the one hand, we really have to deal with the introduction of low carbon technologies or fuels. On the one hand, we really have to push for new technologies, which can be an opportunity in regions that have a lot of demand growth. So we talk, for example, about China, India in particular. So there's really the opportunity to avoid the kind of mistakes that we've seen in some of the industrialized countries to directly leapfrog to low carbon technologies. Also, the challenge there will really to ensure that the financing is in place, that different sectors or consumers can afford these low carbon technologies. If you look at industrialized countries like Europe or the US, there, as you've also seen, we see rather stagnation of energy demand, thanks to efficiency improvement that already happened over the last decades. But there, the challenge is more to how to cope with the existing stock. Stock means there in the power generation we talk about capacity, but also, for example, the building stock in the residential sector. So there, the challenge is more how to define or facilitate the transition from the situation today, reducing the lock-in also when we build new plants to a low carbon economy.
Okay, thank you, Uwe. I think we want to go for one more question, and in the mitigation graph that you showed before, industry did not seem to use renewables. It shows only CCS efficiency and fuel switching.
Yeah, that's maybe a bit misleading. We haven't broken out renewables explicitly in that graph of the analysis. But it rather, we see renewables playing a role in the industry sector, for example, in power fuel switching. So it means there we talk about use of biomass in the sand sector, but also, for example, using biomass as feedstock in the chemical or petrochemical sector. There are opportunities to use biomass, for example, and also we see clearly the pulp and paper sector. If, for example, if we use their CCS, it's based on biomass. So there's also, for example, also opportunity to create in the pulp and paper sector to combine with CCS even negative emissions, so removing carbon from the natural carbon cycle.
Okay, thank you very much. I think I would like to draw some conclusions on this, that to achieve a cost-effective transition to a low-carbon energy system, basically a portfolio approach based on different low-carbon technologies is needed. So across all energy sectors, namely supply, transformation, and end uses. So but the global outlook analysis showed is that this transition ultimately can be possible with currently deployed or near commercial technologies, and this deployment is far from being economically unsustainable. In fact, one of the findings that we had as a result of an overhaul of our investment methodology is that we were able to estimate that the additional investment costs of the 2-degree scenario relative to a reference scenario based on current policies, which is the 6DS that you have seen in some of the slides, would amount only to less than 0.2% of the cumulative global GDP between 2015 and 2050. So one could think that the 2-degree scenario is an economic no-brainer, but still this will not happen by itself. In fact, it will require policymakers to take on the challenge of accelerating clean energy technology deployment. And so the impetus gained after COP21 will need to be translated into effective policies. So with that said, I'd like to move into our thematic focus and introduce you the next speaker, Eric Massanet, which will walk us through the main findings of the systems analysis on cities, and then which will then be described at a more granular level in the following presentations. So Eric Massanet leads the IEA's Energy Demand Technology Unit, which analyzes technologies and policies for the global buildings, industry, and transport sectors. Eric also coordinated the urban energy end use analysis for ETP 2016 and is the lead author of Chapter 3. And Luis Munuera also authored a section of the same chapter. Eric, the floor is yours.
Thank you, Daniele, and good afternoon to everyone joining us on the webinar. As you'll see in today's presentation of ETP 2016, the world's urban areas can play a decisive role in the transition to a cleaner energy future. While doing so, cities can also improve national energy security and resilience while delivering multiple benefits for the environment, human health, and economic growth. In this presentation, I'll try to set the scene for why the transition to sustainable urban energy systems should be a top priority for both national and local governments. I'll also review some key trends and drivers that put cities in the front line for cutting global carbon emissions. I'll discuss the ETP 2016 approach for analyzing the role of cities in global energy systems, and I'll present some results that demonstrate the critical role that cities really must play in accelerating clean energy technologies to meet the world's energy and climate goals. So we live in a world that's becoming increasingly urbanized. As you'll see here in this graph, as of 2013, just over half the world's population was concentrated in urban areas. That's about 3.8 billion people currently. By 2050, however, another 2.5 billion people will be added to the world's urban areas, accounting for the vast majority of global population growth, as you see here. In 2050, 2 out of every 3 people will live in cities. Most of the urban population growth will occur in developing and emerging economies. By 2050, the urban populations of India, China, and Africa alone will account for roughly 1/3 of the world's total population. Rapid urban population growth will also occur in many of the non-OECD economies, driven by strong urbanization trends in Southeast Asia and Latin American economies in particular. As we know, the provision of energy services is critical for ensuring prosperity and quality of life. In order to address these needs while also meeting global energy and climate goals, a transition to sustainable urban energy systems is an imperative, and in developing countries and emerging economies in particular. Urban areas are also the world's economic engines and will continue to play a dominant role in global GDP moving forward. As you see here, the majority of global GDP currently is generated by economies that are highly urbanized. In 2013, around 3/4 of global GDP was generated by countries that had at least 80% of their economic activity concentrated in their cities. By 2050, global GDP will more than triple, and the vast majority of this growth will be driven by cities. In 2050, our original ETP 2016 analysis suggests that urban areas will account for around 85% of global GDP, or about $285 trillion US. Similar to what we saw with the population trends, the majority of urban GDP growth will occur in developing and emerging economies, and in China, India, Africa, and other non-OECD economies in particular. The dominance and growth of urban GDP have at least 2 important implications for the future of energy use. First, economic activity is typically strongly correlated with demand for energy services, and this means that the world's urban areas will hold significant influence over future global energy demand. Second, growth in urban GDP will also increase the prosperity of urban inhabitants, which historically has led to higher per capita consumption of goods and services, leading often to greater per capita energy demand. So just how important are the world's cities when it comes to energy demand and carbon emissions? ETP 2016 presents some new analysis results that can help answer this important question. As you see here, in 2013, total global primary energy use was around 570 exajoules, with results shown here summarizing the direct fuel inputs into each major sector. Our analysis finds that the world's urban areas currently account for roughly 2/3 of global primary energy use, with urban direct energy use dominated by the heat and power generated for use in urban areas, followed by urban buildings, industrial plants, and transportation activities. When we take those direct fuel inputs into the power sector and distribute them to the end-use sectors on the basis of their consumption of electricity and heat, we can see that the buildings and industrial sectors emerge as the largest total, meaning direct plus indirect, contributors to urban primary energy use, followed closely by the transport sector. The sizable contribution of industry to the ETP 2016 estimates can be explained by substantially urbanized industrial activities occurring in some of the world's largest economies, including China, the United States, the EU, Brazil, Russia, and India, to name a few. Following a similar approach for carbon emissions, ETP 2016 estimates that the world's urban areas accounted for around 24 gigatons of CO2 emissions in 2013, or around 70% of global energy-related CO2 emissions. These results make it quite clear that the world's energy future is really linked to its urban areas, and that strong policies to accelerate clean energy technology deployment in cities will be critical moving forward. But in order to have more effective policies to boost clean energy deployment, we also need to look at technologies and policies from a geographical perspective. In fact, urban areas and emerging and developing economies hold the key to the global sustainable energy transition. Our analysis finds that final energy demand will grow by 1/3 out to 2050 in non-urban areas, but by 50% in urban areas. However, there is significant regional variation. In developed economies, urban final energy demand in 2050 is at roughly the same level as it was in 2013. In emerging and developing economies, however, urban final energy demand doubles. Urban final energy demand doubles by 2050 in the 4DS. This means that urban areas in emerging and developing economies are critical to global energy sustainability, as they will account for at least 2/3 of the growth in global final energy demand between 2013 and 2050. Additionally, between now and 2050, 50% of all new buildings, which is equivalent to 40% of the world's current building stock, will be built in cities in emerging and developing economies, which will also account for 85% of the increase in urban passenger transport globally. But since many of the urban areas in these economies still need to be built, we can still avoid locking in energy-intensive urban forms as was done in many currently existing cities. The transition to sustainable urban energy systems can also deliver much-needed improvements in urban air quality. In this graph, we see a summary of recent data from the World Health Organization, or WHO, for ambient PM10 emissions in select cities and from developed, emerging, and developing economies alike. In most of these cities, air pollution levels have significantly exceeded WHO air quality guidelines. In fact, according to the WHO, 88% of people in cities that report on air quality are exposed to air pollution levels in these air quality guidelines. These suggest that much work remains to protect air quality and human health in many of the world's urban areas. However, systems can reduce air pollution from every sector. For example, by reducing energy demand through energy efficiency, by shifting to renewable and cleaner burning fuels, and by deploying zero emissions vehicles, to name just a few strategies that we'll highlight in ETP 2016. At this point, I would also like to call your attention to an upcoming IEA World Energy Outlook special report on energy and air quality, which will be released in just a few weeks later this month. While cities can clearly benefit from the adoption of clean energy technologies, they can also play a very unique role in accelerating global clean energy technology research, development, and deployment. Given their high concentration of people, economic activity, and demand for energy services, cities can serve as living laboratories for the early adoption of advanced energy technologies and policies, giving them a really critical role as global innovation hubs. One example highlighted in ETP 2016 is the Yokohama Smart City Project, which has been rolled out in Japan's second largest city. It represents an innovative public-private partnership between the Japanese government, the local city government, and the many leading technology companies shown on this slide. The project uses smart grids and a centralized energy management system, or CEMS, to manage the energy needs of households, factories, buildings, and local communities. It introduces large-scale renewable energy and promotes next-generation energy storage and transport systems to demonstrate new urban management forms. Such partnerships are really good for both national and local governments, as well as for businesses, as they can stimulate the national economy, create jobs, and offer valuable real-world test beds to companies to further enable technology improvements. As you'll see in the remaining webinar presentations, ETP 2016 takes a systems approach to understanding urban energy use and for identifying clean energy technology pathways that leverage the unique systems advantages that cities can offer when they provide their energy services. Our analysis also recognizes that urban forms can influence a city's energy use for decades to come, and stresses the strong need for national and local policymakers to direct technology investments, enact policies, and pursue urban plans that will lock in pathways towards the most sustainable and efficient urban energy systems, and most urgently in developing and emerging economies where most urban growth will occur. ETP 2016 stresses that compact and livable urban forms are among the most important drivers of urban energy sustainability, and it quantifies the energy and emission savings potentials of the shifts to public transportation systems and integrated district heating, cooling, and power systems that compact urban forms can help realize. ETP 2016 also quantifies the potential of cities as enablers of renewable energy through such strategies as large-scale deployment of solar PV, energy recovery from urban waste streams, and deployment of smart grids, as well as renewable energy procurement. Importantly, our analysis also envisions a significant role for urban electric vehicles coupled with low-carbon electricity sources in abating CO2 emissions from the global transport sector. Last, certainly not least, as you'll hear in the next presentation, high-efficiency buildings represent another major opportunity for policymakers to accelerate the transition to sustainable urban energy systems. Our recommendations recognize that cities are complex systems with numerous drivers of energy use, and that there is no one-size-fits-all approach to sustainable urban energy system policies. For example, our analysis of city data sets underscores the important influence that a city's current housing characteristics and population density can have on the per capita energy use of its inhabitants, and stresses the need for more compact forms to abate growth in urban energy use moving forward. Such forms can be realized in existing cities through urban renewal and redensification, and in rapidly expanding cities through proper urban planning at the outset. As mentioned earlier, our projected growth in urban GDP may lead to increased per capita energy consumption and CO2 emissions, making provision of efficient and low-carbon energy services an imperative for rapidly expanding cities in the developing and emerging economies. A city's climate also has a significant influence on its demand for heating and cooling, leading to differences in the most effective technologies and policies across cities with different climate types. As you'll see in the next presentations, ETP 2016 presents a wide portfolio of recommendations that can be tailored to different cities based on their most important energy use drivers and policy objectives. Our analysis shows that through strong policy actions and accelerated deployment of clean energy technologies, the world's cities can significantly decouple energy use and CO2 emissions from rapid economic growth and population growth. More specifically, our 2-degree scenario demonstrates how the world's cities can increase urban economic activity by a factor of more than 3 by the year 2050, and increase urban populations by 67% to a total of 6.3 billion urban inhabitants globally, while keeping urban primary energy demand nearly steady and drastically reducing total urban CO2 emissions to levels consistent with the 2-degree scenario by the year 2050. Moreover, when viewed in the context of global emissions, ETP 2016 shows that urban energy systems are truly at the heart of the world's low-carbon transition. Unless more ambitious policies are put into place, urban energy-related CO2 emissions will increase by 25% or 20%, by the year 2050, while emissions in emerging and developing economies would almost double over the same time period. Importantly, current urban development trends in the ASEAN countries, China, and India would eat up half the entire CO2 budget in the 2DS by 2050. Achieving the 2DS will require a strategic contribution from urban areas, which can make the transition to a low-carbon energy sector possible, as changes in urban energy systems account for 70% of cost-effective carbon emission reductions in the 2DS. Carbon emissions from urban energy use would be reduced by 60% by the year 2050. This urban low-carbon potential lies in compact urban development, energy-efficient buildings, public transport, travel demand management, electric vehicles, and distributed renewable energy and smart energy networks. I'll now turn the presentation back over to my ETP colleagues who will discuss these opportunities and their associated policy recommendations in greater detail.
Thank you very much, Eric. I think the conclusion that basically local and national policymakers need to increase their efforts and work together, and so as to ensure that the right level of vertical integration can ultimately enable cities to meet very ambitious goals is a very relevant one in the current policy environment, and we'll get back to that with the policy presentation which will be at the very end. So with that said, I'll introduce you to our next speaker and presentation. So as we have seen in the global outlook presentation, the building sector accounts for roughly 1/3 of both global final energy demand and also CO2 emissions if the indirect emissions from power are considered. And we know that there is a vast and largely untapped potential to reduce energy consumption in buildings, but what are the specific levers that urban areas can have to reduce buildings' energy consumption and carbon emissions? So this is one question that came out during the scoping analysis, and that with that said, I will hand the floor to John Dollock, which is the building sector lead for ETP and developed the concept for the ETP 2016 project. John, the floor is yours. Thank you.
Thank you, Daniele. So for the ETP 2016 analysis looking at buildings, very similar to the work that we did in our end-use sectors for transport and industry, our first challenge was to estimate the rough energy consumption in terms of final energy that is consumed in the end-use sectors in urban areas, as explained by Eric previously. In the building sector, we estimate that total final energy consumption in urban buildings accounted for roughly 78 exajoules in 2013, out of roughly 120 exajoules for the global building sector, meaning that more than 60% of total building energy consumption in 2013 was consumed in cities. Now, urban buildings in non-OECD countries consume, as you can see here, almost as much as urban buildings in OECD countries, where obviously the bulk is happening in developing countries and emerging economies. There are some stark differences across OECD urban buildings and non-OECD urban buildings, particularly with regards to final energy demand and the end uses in those buildings, particularly with regards to space heating in OECD countries, which are typically in much colder climates, and with cooking and water heating, which are still very large end uses in buildings in developing countries. Now, 65% of space heating in OECD countries, 65% of final energy consumption in buildings in OECD countries is for space heating and cooling. So the important target in this sector for developed countries is obviously targeting the envelope of buildings, as well as addressing particularly renovations in building envelopes to reduce that energy consumption. In emerging economies and the non-OECD world, this is quite a different picture, where the bulk of building additions to 2050 will be in new construction, meaning that there will need to be significant emphasis placed not only on the construction and the efficiency of that construction, but also the choices for the equipment that goes into those buildings. This is also particularly true as the building loads, as I mentioned, are different in those countries, and we're changing demand, particularly for thermal comfort, and in many non-OECD countries for space cooling is rapidly increasing. Another difference between OECD and non-OECD urban areas is biomass, where traditional use of biomass is still very common in many non-OECD countries. As those developing countries and emerging economies shift off of biomass to many modern commercial services, we should also ensure that they are moving to the most efficient equipment choices to ensure that the growth does not replicate energy patterns in many developed cities. Now, looking forward to 2050, urban building energy consumption in a business-as-usual scenario, or 6 degrees Celsius scenario in ETP 2016, grows by about 70% over 2013 levels to about 135 exajoules, meaning that more than 90% of expected energy growth in global buildings is likely to occur in urban areas. As you can see in the lighter colored bubbles here, in developing countries or non-OECD countries, urban building energy consumption more than doubles by 2050 as demand for energy services and comfort continue to increase, as well as with increased urban populations. Under the 2DS, urban building energy consumption decreases by more than 1/3 when compared to the 6DS in 2050. And this essentially accounts for 75% of global building energy savings, meaning, of course, that urban areas will play a critical role in achieving the energy efficiency targets for the building sector. As you can see here in the two bottom green bars on the bar chart, the bulk of those savings, or roughly 40%, are also coming from space heating and cooling, again pointing to the need to address both renovations in existing buildings and highly efficient new building construction in developing cities. This decline, of course, needs to be paired as well with high efficiency equipment, as well as with minimum energy performance standards for different appliances, lighting, and equipment in buildings to ensure that we achieve the 2DS targets seen on the far right in this graphic. Now, as I mentioned, space heating and cooling will play a particular role in achieving the 2DS targets, and in developing countries in particular, addressing space cooling will play a major role in achieving energy efficient buildings. Growing household wealth, and again, as I mentioned, continued growth in demand for thermal comfort in buildings will contribute to significant growth for space cooling in cities in the developing world. Globally, space cooling increases more than 3 times over 2013 levels in the 60s to 2050. In rapidly emerging and hot and humid climates, for example, India, Indonesia, and Mexico, urban space cooling demand could increase as much to 5 or 10-fold over 2013 levels by 2050. With nearly 1 billion new households expected in those urban areas in non-OECD countries by 2050, these countries will absolutely need to implement more rigorous and enforceable building codes to ensure that those thermal loads do not grow to the level seen here in the 6DS, and that we achieve energy efficiency targets as outlined in our 2 degrees Celsius scenario. In terms of emissions from the building sector, under the 6DS, urban CO2 emissions would increase from roughly 7.5 gigatons in 2013 to nearly 12 gigatons in 2050. If we were to tap into the energy efficiency potential available in the building sector, much of which, if not most of which, is available on the markets today and already cost-effective, we could drastically reduce these emissions. Nearly 65% of urban CO2 reduction in the 2DS would come from the residential subsector, which represents nearly half of the global building sector emissions reductions potential to 2050. Overall, when combined with urban services buildings, urban buildings account for nearly 80% of CO2 emissions reductions in 2050, again highlighting the importance of cities in achieving the 2DS objectives. When looking at the role of energy efficiency in buildings, it's also important to take into account the considerable importance that urban buildings will have on the impact of energy consumption when power generation is considered. Urban buildings are estimated to have accounted for nearly 80% of total building electricity and commercial heat consumption in 2013, and the bulk of electricity and commercial heat growth to 2050 is expected to come from cities. Looking to 2050, energy efficiency measures, including efficient equipment as well as improvement in the thermal envelope of buildings, account for roughly 1/3 of the indirect emissions reductions in buildings, as shown here in blue. Improved efficiency and reduced building electricity and commercial heat will therefore not only contribute to reducing overall building electricity and commercial heat, but also allow for a more efficient, more resilient, and lower carbon energy grid. Energy efficiency and fuel switching in urban buildings can also contribute to numerous multiple benefits in cities, including improved living conditions, such as improved thermal comfort in buildings, as well as improved air quality in cities, as mentioned by Eric. Since heating and cooling play such a significant role in the energy efficiency and emissions abatement potential in the building sector, a critical part of the ETP 2016 analysis looked at buildings not only as elements within a city, but elements as part of cities. In this sense, we looked at the potential for buildings interacting with the grid and what contributions the combinations of buildings, when paired with electricity, commercial heat production, could have in an energy efficiency scenario looking forward. As I mentioned, 40% of energy savings in cities come from space heating and cooling, which relies heavily on more efficient building envelopes, as well as more efficient heating and cooling equipment. Now, as I'm sure many of you know, the achievement in new construction, and in particular in building renovations, of very low energy efficient building envelopes can be very difficult, and in many situations can also be quite costly. As part of the analysis in ETP 2016, we looked at how some high-performance building options, such as near-zero energy buildings, may be difficult to achieve in dense urban areas. Building envelope renovations also are not at current renovation rates in line with 2DS in most of the developed world. However, urban areas provide a unique opportunity to provide low-carbon heating and cooling solutions through buildings integrated with district energy networks. As part of this analysis, we've included 3 case studies in ETP 2016 looking at integrated buildings in Stockholm in Sweden, Turin in Italy, and where in all 3 of these cities, the analysis looked at what the cost-effective energy abatement and carbon abatement potential would be in buildings with regards to the same energy efficiency and carbon potential in district energy networks. As an example here in Stockholm, this analysis pairing both building energy measures as well as anywhere from standard to advanced carbon abatement measures within the district energy network look like in terms of both the energy savings and emissions reduction potential, as well as the life cycle costs for those integrated building and district energy network measures. The interesting conclusions coming from this study are that combinations, and again depending on the city, of moderate to advanced building energy efficiency measures with typically advanced district energy network measures in terms of carbon abatement would be the most cost effective, as seen in the 2 bottom bars here. The reason this is important is that if the continued rates of energy efficiency in building envelopes are not achieved, we would need to significantly increase the savings and emissions abatement in the district heat network. However, looking, for example, at Stockholm, if we strategically plan these measures over time, where we are addressing both the carbon emissions produced from the district energy network as well as the efficiency of buildings, we could not only achieve the greatest energy and emission saving potential, but also at prices that are either at or below the life cycle costs for a business as usual scenario. Looking forward, of course, as was mentioned, in order to move the building sector forward and achieve these energy efficiency and carbon abatement potential, the first actions needed are to put the building sector on the right pathway and implement across all countries rigorous and mandatory codes to ensure that new construction is built to the highest efficiency standards possible, and to ensure that renovation rates of existing buildings in the world are more aggressive as well as more performant in terms of the energy efficiency gains made. Key policy actions in the building sector can deliver significant energy savings and emissions reduction by stimulating widespread deployment of energy efficient technologies. Of course, improving and adopting the enforcement of mandatory policies for low-energy new building construction is a necessary first step for all countries, and improved building capacity, including education and training, is still needed in many countries to ensure that building energy code compliance is standard practice. In OECD countries in particular, building renovation measures for existing buildings is crucial, where the bulk of building stock today will still be standing in 2050. To achieve 2DS objectives in the building sector by 2050, a global race to the moon approach is needed to bring energy efficiency for renovation and new construction from small-scale demonstrations to mass market at cost-effective pricing. With national support, urban areas can lead on the critical task of adopting, monitoring, and enforcing building energy codes for new construction, as well as a global uptake of deep energy renovation of existing buildings. Globally, increased efforts are also needed to achieve high market penetrations of energy-efficient building technologies, including envelope technologies such as high-efficiency windows and insulation, as well as equipment within buildings, appliances, lighting, and other services that are used in the building sector. Cities can support this through local awareness programs, incentives, energy performance rating and reporting schemes, as well as engagement with local building stakeholders. And all of this can help to ensure that efficient products are not only made available, but are used as standard practice. Last, the integration of energy-efficient buildings and modern district energy networks using combinations of different technologies such as heat pumps and renewable energy, thermal storage, as well as other low-carbon heat sources, for example, industrial excess heat recovery, can help put urban building sectors and the global building sector on a sustainable, energy-efficient 2DS pathway. Further research and demonstration of district energy network modernization and the effects of deep efficiency improvements in buildings is still needed, but as demonstrated in ETP 2016, these are possible using using technologies that are mostly available on the market for more advanced technologies in the market and demonstrating their effectiveness. And with that, I hand it back to our ETP project lead, Daniele Grapponi. Thank you.
Thank you very much, John. I think that one of the interesting takeouts is that higher density is one of the enabling factors for low carbon urban buildings, but also for the transport sector, as we will learn shortly from our next speaker, which is Pierpaolo Cazzola. Pierpaolo is the transport sector lead and is coordinating the activities of the Mobility Model Partnership, and will discuss the sustainable urban mobility analysis of ETP 2016. Pierpaolo.
Thank you. Hello, everyone connected. I will try to walk you through what we have done for the analysis of sustainable urban transport for ETP 2016. So my colleagues have already mentioned the focus on urban aspect of ETP, the policy objectives, so environmental sustainability, energy security, economic development, and the fact that we have tried to develop an analysis on how local and national energy policies can be aligned to actually meet these objectives. In the case of transport, the way we did it is by looking first at estimating what is the share of urban and non-urban transport activity, energy demand, and greenhouse gas emissions, and then by making projections on how things would develop within and outside of cities, and then we looked at what are the available technology options and giving it a focus primarily on those that would deliver on the policies that would be able to transition towards this increased sustainability in transportation. So, by the way, the sequence of what we have just mentioned in terms of analytical steps for the transport chapter is also the sequence I'm going to follow in this presentation. First of all, so we look at the status quo in the base year in 2015, and Here you have a slide on passenger transport activity across the main areas of the world that we have been analyzing thanks to our mobility model. So the pie chart, the size of the pie chart shows this, the amount of passenger kilometers taking place in the different regions, and the different colors used for the pies reflect the relative importance of different modes, and this is for the national level activity. So the key take-homes for this is that most of the OECD economies are dominated by aviation and cars, with relatively minor shares of rail and public transport, especially in North America. Rail plays a major role in countries like India, China, Japan, and to some extent also in Europe, and is also non-existent in Latin America. The diversity of options for mobility in Asia is much larger, reflecting the fact that the average income is lower, and so the choices don't fall on the fastest and most expensive modes. Finally, there are regions, especially Africa, where there's a major share of buses and minibuses or collective transport, due also to partly to the fact, to a major extent, to the fact that average incomes in Africa are the lowest in the world. Once we look at how this transforms, once we move it into energy demand, so this shows that the domination of cars and aviation is even stronger in the case of OECD, and that's because cars and airplanes are the most energy intensive modes, so they not only have a very large share of activity in the OECD, but also they become more dominant in energy terms because this activity gets multiplied by the highest energy intensities. So that, generally speaking, means that the share of cars and aviation in terms of energy demand is higher also in the non-OECD. Nevertheless, in the OECD, we also see a significant, sizable amount of energy which is not allocated to cars, namely for urban energy. There is a major contribution from two-wheelers, and that's primarily taking place in Asian regions. Another important element that you may not see on this graph, but it is going to be apparent soon, is that actually the amount of energy used by two-wheelers in urban exceeds the amount of energy used by light commercial vehicles and medium trucks. For freight transportation modes, for non-urban and urban, and for world OECD, non-OECD. The key take-home in terms of activity is that urban activity is confined basically to light commercial and medium trucks, and is about 100 times smaller than non-urban activity, which is primarily due to shipping, rail, and heavy trucks. Once we move into energy demand, the fact that light commercial vehicles and medium trucks have a high energy intensity per unit, so per ton kilometer, means that the 1% share that they have in activity becomes a 20% share in energy demand. So that's a sizable amount, and shows the importance of urban action also on the freight side. The last slide about the baseline, so 2015, concerns an estimation of well-to-wheel emissions for emission intensity, absolute emissions, for the different modes, and looking together at passenger and freight, and urban and non-urban. These slides also shows different components in CO2 emissions, so well to tank and tank to wheel, so basically showing what is imputable to burning the fuel in the car or manufacturing the fuel before delivering it to the transportation vehicles. The total amount of well-to-wheel emissions imputable to transportation is 9.5 gigatons of CO2 equivalent. We see that the dominant mode remain passenger cars, followed by aviation, but also heavy trucks and shipping. So in terms of magnitude, urban cars and then non-urban cars, aviation, heavy trucks and shipping are the most relevant share in CO2 emissions in the Bay Area. If we project emissions into the future, we have the three different scenarios which have already been introduced in terms of characterizations for 2DS, 4DS, and 6DS. In the Bay Area, we have 107 exajoule consumed, and the range that we have for 2050 in total is between 100 exajoules and 184 exajoules, with the lowest value being for the 2DS scenario and the highest for the 6DS scenarios. So in 2DS, we actually have a global decline, even though this decline doesn't take place in all regions, and I'm going to speak about that in a minute. There is an increased diversification of energy demand in all scenarios, and of course this is far larger in the 2DS case. And electricity and biofuels, where electricity and biofuels become important substitutes for oil-based fuels. Natural gas has some uptake in medium and heavy truck and shipping, but it's not a game changer for greenhouse gas emission reductions. It has a higher relevance for the reducing local pollutant emissions. Here you have outlooks in the different scenarios for the major global regions. I think what is important here is to see that OECD regions have a stabilization of energy demand in 6DS and actually a net decline in 4 and 2DS scenarios, while non-OECD regions tend to have an increasing demand in 6DS and only, and in some cases reach a peak in 4DS. And in most cases also peak in 2DS, but not in all cases. For instance, Africa does not peak also in case of 2DS scenarios, and that's primarily due to the different point in the development patterns that the different regions have and how this links with the uptake of different transport modes. The high-level message is that we need decouple activity and emissions if we need to meet 2DS targets. This slide has been shown at the beginning of the webinar as well, and reflects CO2 emissions in OECD and non-OECD by looking at different wedges that can actually bring us from 6DS to 2DS. In the OECD, emissions basically stabilize already in 6DS, reflecting what happened also in terms of energy demand. And then they are brought down by three main type of instruments. So avoiding or shifting emissions, avoiding emissions thanks to avoiding part of the transportation activity, for instance, because of densification. Shifting to less energy-intensive transport modes, and then making vehicles more efficient and making the fuels used by the vehicles less carbon intensive. So broadly speaking, the technology analysis that we carried out reflects these three main areas of intervention, so avoiding and shifting emissions. So we looked at technologies that actually allow to travel demand. We looked at technology to improve the energy efficiency of vehicles, and technologies that allow to reduce the carbon intensity of fuels. For the sake of time, I'm going to focus primarily on the vehicle technologies and on the mode which is subject to some of the largest changes between 6DS and 2DS, which is a case of cars and light commercial vehicles. So the outlook in 6DS is rather conservative. We have fuel economy regulations that actually do not translate in on-road movements because of the lack of compliance, and we also have more than 3 billion light-duty vehicles by 2050. The moment we move into a scenario which is 4DS, actually the fuel economy regulations are met, we see a significant uptake of hybrids, and if we have tighter fuel economy regulations and other policies that lead to, that basically increase the pressure for decarbonizing transportation. We have a significant uptake of technologies beyond the hybridization, enter into hybrid and electric vehicles. By 2030, battery electric vehicles and plug-in hybrid electric vehicles reach 10% of the light vehicle stock, and by 2050 they reach 40%. The leading markets in which they actually penetrate are OECD markets, namely Europe, Japan, United States, and China. On the fuel side, there's a significant increase between 4DS and 2DS. So what you see here on the slide are top right 4DS, bottom right 4DS non-urban demand, and then top left graphic urban DBS, bottom left graphic non-urban demand in 2DS. So you see that alternative energy carriers to fossil fuels have a much higher uptake into DS, even if overall there's a lower energy demand, and that there is more than twice the urban demand in 2DS and in 4DS, and more than 3 times the non-urban energy demand in 2DS and in 4DS. The main differences are due to the different type of biofuel uptake. So in 2DS, we only see an uptake of advanced biofuels, which in the case of 4DS, they do not become cost competitive. And also we see a significant uptake of electricity, primarily reflecting the high share of electric vehicles entering the vehicle stock. The policies that go these kind of changes, or that lead to these kind of changes, come from a portfolio of instruments that combines national measures and local measures. Sometimes national measures may be supranational measure. That's the case, for instance, of economic standards in the European Union, where they are actually enacted at the EU level, not at the country level. But the national measures that we looked at and we took into account include fuel taxes, the removal of fuel subsidies, and the introduction of CO2 taxation in particular. So not just limited to the removal of fuel subsidies, but going beyond that. Include also fuel economy standards, vehicle taxes, which have a major impact also at the local level and in urban environments to actually shift mobility towards public transport modes. And in the case of limiting the scope of these to vehicles, they need to include bonus-malus or rebate schemes to promote more efficient technology. We look also at R&D support, of course, to help cutting costs. In terms of local measures, we took into account compact city policies, so policies leading to urban densification and the integration of land use and transport planning. For instance, through the promotion of transit-oriented developments. We also look at pricing policies, regulatory policies, and public transport investments, which are required to make public transport more appealing. Here you have a table where there's a list of the policy tools that we took into account and the areas where they have an impact. So the main messages here is that most of the local policies have impact on shifting mobility from energy-intensive modes, namely cars, and towards public transport, so less energy-intensive modes. And to some extent, they can also incentivize the uptake of less energy-intensive or less carbon-intensive vehicle technologies. For instance, if you have restricted access, so if you have waiver on access to bus lanes for electric cars, that's one incentive to increase the uptake of electric cars at the local level. National policies have primary importance to deliver vehicle efficiency improvement and increased uptake of low carbon fuels. The rationale we used to actually define what are the different policy tools that can actually deliver in the case of urban areas are the following. So first of all, we observe that income growth tends to be coupled with increasing share of passenger kilometers on cars. We saw that public transport shares in high-income countries are clustered in different groups. Basically, in countries with relatively low fuel and vehicle taxes, they tend to be very low, while in countries that have higher fuel taxation and higher vehicle taxation, they are the share of public transport share is significantly higher than in countries with similar incomes but low fuel and vehicle taxes. And so we use these to suggest that vehicle taxation and fuel taxation have important impacts in perspective in making sure that the uptake of public transport will remain significant. Urban density also emerges as a key prerequisite to provide mobility, alternative mobility. So basically, without increasing density, we cannot see a significant share of public transportation, because basically there are no walkable neighborhoods, and there's no incentive for people. So there's no incentive even to supply public transportation, because it would make it having prohibitive costs in order to stimulate people to actually take up public transport. So the reasons why we identified compact cities as compact city policy densification, TOD, as important element in the policy narrative at the local level is that without this density requirement, it is basically impossible to see an uptake of low energy intensity transportation modes. So the combination of the policy recommendation builds on these and on the messages identified by including economic incentives, so driven by fuel and vehicle taxation, to increase the appeal and effectiveness of public transportation in cities. The analysis built on examples of measures which are already in use to a large extent, and on examples taken from specific cities which are currently front runners. So the effects that have already been observed in these cities were instrumental to actually generalize the impact on other cities and other regions, and underpin the results that we have in our projection and in our policy recommendations. Overall, I would say an important message is that basically all these policies aim at making sure that transport emissions peak and were set to a point. So they were driven by the idea that they would need to peak and decline within the next 10 years in order to meet long-term greenhouse gas emission reduction targets that could be compatible with meeting the 2DS target and the 2DS carbon budget, given also other results in the ETP analysis, so results from other sectors pointed out. That's it for me. I think we're happy to give the floor to Daniela.
Thank you very much, Pierpaolo. So far on, we have a focus on the demand side of urban energy systems. However, on the supply side, one might want to ask to what extent can cities meet their energy demand with local urban energy sources, and how can the industry sector can turn to be from a consumer to an actual provider of energy through excess heat that is normally generated in industrial processes, and also what extent can smart urban energy networks be capable of integrating local energy sources and provide a range of sustainability benefits. So with that said, I'm going to introduce you to the next report, which will actually include 3 sections with 3 different presenters. The first one is Uwe. Uwe Remme is for the ones who have just joined the webinar, is an energy analyst in the ETP team, where he leads the energy supply side modeling and is coordinating the ETP scenario analysis. Araceli Fernandez is the energy technology analyst within the ETP division, and she is responsible for energy-intensive industry-related analysis. Luis Munuera is also an ETP energy technology analyst, where he leads the smart grids and system integration analysis. So, Uwe, Araceli, and Luis, the floor is yours.
Yeah, thank you very much, Daniela, and also good afternoon to everybody who's just joined us now. Yeah, I want to talk a bit about energy supply in cities, and as we've seen in the previous presentations on buildings and transports, cities are and will be even more in the future be centers or where energy demand is concentrated. Many of the energy consumed in cities actually needs to be typically imported. For example, if we talk about transport fuels like gasoline or diesel, but there also will be opportunities to use energy sources within or close to cities to cover part of the energy demand that's needed by urban areas. Example on the electricity side are, for example, rooftop PV or the use of waste-to-energy plants. So we were burning municipal solid waste to produce electricity or district heating or also district cooling. And for heating and cooling purposes alone, one can think about using thermal water heating, which is already a very competitive technology in many parts of the world, or to use the ground beneath the buildings for geothermal heating or environmental heating, and also for cooling purposes of buildings. So one can also take advantage of resources not directly in the city, but we can also look a little bit beyond the city per se, meaning we're looking in the vicinity of the city, we're looking at peri-urban areas, and there we can also look at opportunities, for example, to look at utility PV plants, as shown here in the figure, although Araceli Fernandez will talk about that in a few minutes. In ETP, we did not attempt to do an exhaustive analysis of all the options of local energy sources, and this was rather focused on some of the options that we think can become important or key for cities on the electricity and heat side. Meaning for electricity, we looked at rooftop solar PV. For electricity, but also district heating, we used the use of municipal solid waste to energy plants. Then, as I mentioned, for more in the peri-urban area, we looked at industrial excess heat, that's source for district heating, or again, a combustion heat pump for district cooling. And in addition to looking at the supply of energy resources in cities, cities can also be innovation hubs, given the concentration of various demand services in buildings and transport. So meaning they can facilitate also better integration of different energy vectors across sectors. For example, could lead not only to increased efficiency or reduced cost and emissions on a local level, but can also provide additional benefits to the wider energy system, also at national level. Example is here, for example, is the use of electric vehicles through smart charging, so that this possibility for demand response can also provide variability or flexibility to the electricity system for the integration of various renewables. So in that sense, cities can also play a role in contributing to some of the challenges that we see in the transition to a low-carbon energy system in the future. So to start with, I would like to give you an overview about the estimated technical potentials for mentioned supply options on the electricity and heat side. So to start with electricity, you see on the left side a graph showing the global final electricity demand in urban areas or cities in 2050 in the 2DS, which accounts for around 75% of global electricity demand. And electricity becomes by 2050 in the 2D as the largest foreign energy carriers for cities, covering 1/3 of all urban energy needs. For comparison, the estimated share today of electricity covering urban energy needs is around 1/5. The technical potentials we estimated for electricity from solid waste and also sewage gas, which you see here in the graph, are with 30 terawatt-hours and around 190 terawatt-hours respectively, rather small, representing combined just 4% of the urban global electricity needs. But even if these amounts in energy terms are small, the revenues from selling electricity or also heat from municipal solid waste or sewage gas can be welcome additional income for cities to reduce the costs for services like waste management or water treatment that cities have to provide. So in that sense, these options, even if they look small here on the graph, can be very interesting for cities to investigate. And the last option looked at rooftop solar, which is actually the largest option that we largest option with a potential of around 9,000 terawatt-hours, representing around 1/3 of the urban electricity demand in 2050 in the 2 years. On the district heating side, you see again the demand for district heating in the 2 years in 2050, which is much smaller than the electricity. So be careful that scales of the are different in the two graphs, and accounts for 3% of urban final energy demand. So district heating roughly 3% of total urban energy demand on a global level. Again, district heating demand very much also depends on, have to keep in mind, on local conditions in terms of climate, but also, for example, if you talk about infrastructure for district heating, also on heat density, demand density, so that's where urban form also plays an important role in the economics of these distribution networks. If you look at the different potentials for the provided in cities for district heating, we looked at industrial access heat, here abbreviated as IEH, and Rasteli will talk about that in a few minutes. Then if you look at sewage gas, so that's providing also some amount of potential. And we also, in addition to sewage gas, we also looked at wastewater, at heat from wastewater. So that means that that's the recovering or recuperating some of the heat in wastewater streams for heating purposes, either on-site of the wastewater treatment plant, but can also be, if the opportunity is there, could be upgraded with a heat pump and then also fed into a district heating grid. The final option we analyzed is solid waste, which, as you see here, is almost on par, on level with the demand for district heating on a global level. But here one also has to be careful that the regional distribution, that not necessarily all the heat supply that we see here, for example, light green in India, there's hardly any district heating demand in India. So that way one has to be careful that these are really just technical supply potentials, not taking into account the demand structure. Also, for example, still one can make use of this heat in India, for example, as I mentioned before, using instead it for district cooling networks in cities. Following, I would like to talk a bit more about rooftop solar PV. So that's one of the options we analyzed in more detail in ETP. And many cities started actually to assess the potential of their roofs, either solar PV, but also solar thermal water heating. Here's an example from Paris, where they did a detailed analysis on the potential of individual buildings of the roofs in terms of how much solar PV or water heating panels could be installed. In ETP, such a detailed assessment, especially if you want to do it on a global level, is way beyond our capabilities. So we rather took a more aggregated approach to assess the potential for rooftop PV, and that's shown in the right graph. So instead, we reviewed existing assessments of cities to develop a heuristic to describe the rooftop potential, which is shown in the graph. Where available solar rooftop areas in cities can be approximated as a function of population density. So you see here different cities, again highlighted right, Paris, where you see a functional relationship between population density and the rooftop area per capita. Again, be careful here, we have two logarithmic scales. So actually the line here is with a take account when looking at these potential. This relationship in combination on assumptions on development of population densities, and also assumptions or data on solar irradiance lead then to the, they're then also used in the assessment of the solar rooftop PV potential. Admittedly, such analysis has caveats by characterizing the roof area in cities only through one characteristic, a parameter, in this case population densities, and the analysis also takes into account some physical characteristics, for example, like the orientation of the roof area. So there, clearly, we acknowledge that there are caveats in this analysis. Still, we think that such analysis can be helpful to at least provide some insights in the scale of solar rooftop PV potential in different parts of the world. If we look at the resulting technical potential by city size, which is shown here in the graph, one can see that the potential reaches around 9,000 terawatt-hours by 2050, with the increase driven by growing urban population from around 4 billion people in 2050 to more than 6 billion people in 2050. If one also takes into account rural areas, which would increase the potential further, so the rooftop potential also in rural areas, not just urban areas, which would account for additional 5,500 terawatt-hours of rooftop PV potential. As you can see in the graph, small cities below 1,000 people account for around 40% of the estimated potential, and that is due to the fact that there we've got areas with low population densities. As you recall from the previous graph, there are areas where we see higher rooftop PV potential per capita. Overall, we see also that's the reason that we see that urban form is an important factor in the potential for rooftop PV. On the other hand, these small cities, we're talking about 30% of the urban population living in cities below 100,000 people, are often not about able to address some of the challenges to take advantage of the potential. So we see here possibilities or resource limitations in terms of data, in terms of having the personnel that can do this assessment. And so there, regional or national governments can play an important role in addressing, overcoming these kind of barriers or gaps to make sure that the potential that one sees in smaller cities can actually be realized in our 2-degree scenario. If we come to the deployment that we see, or the usage of this rooftop potential that's shown here in the bar graphs for different regions, and at the very bottom in the darker color also for the world. So there we see identified on the global level around 9% of the urban electricity demand could be covered by urban rooftop PV, taking into account the competition with other technologies to cover urban electricity demand. So that's really the kind of economic potential that we identified in our 2-degree scenario. We also see the variation or the range of the share, how much rooftop PV contributes to the urban electricity demand, from shares of 25% in India going down to around 5% in Latin America. And again, there one has to take into account the competition with other options. For example, if we look at the US, there the total contribution from PV to urban electricity demand is around 14%, or so. In the graph here, you see rather a share of around 7%. That's due to the fact that you also see in the US the potential, for example, to use utility scale PV to provide electricity to cities. If one looks also, this graph shows the deployment, but what are the benefits of using rooftop solar PV in cities? We also try to assess the impact on CO2 emissions and fossil energy use. So deployment of rooftop solar PV in cities provides around 9% of the CO2 reductions linked to urban electricity consumption in the 2DS, and that way one can replace about 170 exajoule of fossil energy in electricity generation. And just to give a comparison, a reference for the figure 170 exajoule is roughly the number that's also the accumulated gas consumption in the European Union in our 4-degree scenario between 2015 and 2050. So with that, there was a brief overview of some of the supply options that we see, particularly on the electricity side. With that said, I would like to hand over to my colleague Araceli, who will talk more about industrial excess heat in industry as option to provide heat services in cities.
Thank you very much, Uwe. So indeed, industries, and especially on the area of industrial excess heat, could be an additional source when it comes to supply energy for either urban areas or also neighboring industries through thermal networks. If we really explore the energy that is consumed in an industrial process, not all of that is basically converted into effective energy or energy that is really used directly in the process. Part of that energy really is released to the atmosphere either through hot flue gases or waste gases that leave the process, also hot products, but also through hot surfaces from industrial equipment. So there is a specific part of that thermal energy that could be recovered to be either used directly on site to sustain the process for that industrial manufacturing area. But from an energy efficiency perspective, the first priority should be the avoidance of that excess heat generation, either through an improvement of or reduction of the specific energy requirements of the process, by integrating, for instance, different techniques that could help to understand how different hot sources or hot streams and cold streams could be combined in a process to optimize the energy requirements. As I mentioned, part of that excess heat or excess energy could be recovered. Again, from an energy efficiency perspective, the idea would be that to minimize transfer losses, that heat ideally should be used on site, but it could also be transferred to either a neighboring industrial site or a neighboring urban area in cases where there's not a compatible thermal demand existing in that process. Then lastly, that energy that is recovered on a thermal basis could also be converted into electricity. Then again, to satisfy some of the requirements from the process or also to be exported to local grids. As you mentioned, of course, there's different components when it comes to assess the cost effectiveness or competitivity of different recovery technology options. There's many factors involved in that. One of them would be the quality of that industrial excess heat source related to not only the absolute amount of thermal energy, but also what is the temperature level or XG content of that, and also related to factors such as intermittency, cleanliness, etc., of that heat source. On the other hand, there's other factors to be considered, as what is the distance from the heat source and the heat sink, so where there is a compatible demand for that heat, and whether there is any infrastructure already existing that could be used to deliver or to reach the heat sources from the heat sink. For this edition of ETP, to understand the different supply options for urban areas in this area of industrial excess heat, the analysis that was taken or was performed was a technical assessment potential to understand what could be the additional energy that could be recovered from energy-intensive industries by considering that there were no economic barriers, and what would be the contribution of a wider deployment of different recovery technologies in this type of sectors. One of the components into this is that we've considered commercially available technology options in terms of recovery. The other component is also that we've focused on medium and high temperature excess heat sources, which refer to heat sources which are above 100 degrees C. So just as examples of those results, if we look at the iron steel sector, what we identify globally is that 2 exajoules could be technically recovered from that, the existing stock of production from that sector, which represents 6% of the total final energy use in iron steel making. Within the options that we've looked at when it comes to recovery technologies, that will cover the whole process chain, so from raw materials preparation to the different steps into the iron making and crude steel making and finishing. And the first, or let's say the greatest opportunity that we identified was the use of the sensible heat and the chemical energy within the off gas that is produced in the basic oxygen furnaces. So that was by far the greatest opportunity across regions. When it comes to assess how this technical potential is regionally distributed, we found that around 74% of that is based on non-OECD countries, and that's not surprising considering that about 70% of the crude steel production globally comes from those regions. If we just have another example from another sector that we've explored in terms of excess heat, in the cement sector, we've identified 6 exajoules of industrial excess heat in the same basis, so trying to understand what is the current penetration level of recovery technologies that are commercially available today, and what would be the consequence of wide or let's say further deploying these technologies across the whole stock. So in this case, similarly, there was about this potential represented 6% of the final energy use in the globally in the cement sector as well, with a big contribution from non-OECD countries, also because the great shares of global production, 88% in this case, in terms of production levels. Just to highlight that the recovery options that were considered here, we're looking at sensible heat that could come either from the exhaust gases from kilns or clinker coolers. And in this case, of course, there's a great influencing factor, which is the moisture content of raw materials, which was considered to be between 2 to 6%, which is rather low. So then this potential, of course, will vary across regions depending on what are the actual moisture contents considered, or more, let's say, realistic in practical terms in those regions. So for this instance, this could imply quite a difference if we look at regions where they tend to work with wetter raw materials like Russia, for instance. So these were just a couple of 2 examples. The idea here is that, as it was mentioned, part of this excess heat could be used depending on whether the local conditions are favorable for, or let's say, to contribute to the supply energy mix for urban areas, but also for supplying energy to industrial neighbors where there is compatible demand for this. With that said, I'm just going to hand it over to my colleague, Luis Monuera, who is going to bring you through the smart grids and integration portion of the chapter.
Okay. Thank you, Araceli. So we have seen in earlier presentations how cities will concentrate more and more these demands are also very varied, both in terms of when they are required, where they are required, and also the possible energy sources that can meet them. So, for example, the demand for thermal comfort, for heating and cooling, varies seasonally and daily, whereas, for example, transportation needs, they respond more to daily patterns of use. At the same time, we have the supply side. We have seen already earlier in this presentation how the potential for generating energy within a city is constrained, but it's also very much facilitated by the location and how the built environment has been shaped, so basically the urban form. We have also seen how higher densities can determine possibilities for localized energy sources. They can open them up, but they can also constrain them, like distributed generation from rooftop PV. We've seen waste energy, excess heat from industry, or from buildings, or co-generation of heat and electricity. The key message here is that urban energy networks are really the backbone that allows the exploitation of these important potentials and to deliver them efficiently to meet energy service demands within a city as and when they are required. The new development here is that there's emerging IT systems, technologies, and smarter monitoring and control that are now facilitating this technological change more than ever. So much of the infrastructure for delivering energy has already been built, but we expect the rising demand for energy, particularly in cities, to dramatically drive growth moving forward. When we look, for example, at electricity distribution networks, which is what we see in this figure, when we look at cities in particular, largely driven by growth in developing countries, we see that the total network length will nearly double out to 2050. Much of this is built out of new networks, but as you can see here as well, almost half of the existing equipment and infrastructure will need to be either retired or will need to be replaced within the next 35 years or to 2050. This presents an important opportunity to build infrastructure in a new way, in a smarter way, to accommodate more and more distributed energy and the supply options that we've seen earlier today. A key issue here, however, is that in building, this urban energy delivery infrastructure of the future, urban planners have to contend with the fact that networks are among the least innovative areas in the energy sector. So around 50% of equipment in OECD countries right now is more than 40 years old. This means that new smart technologies have to work with old infrastructure and presents very particular challenges that need to be overcome. So to understand how scaling up of the supply options we analyzed in ETP 2016 would impact the development of energy networks, we developed some conceptual frameworks. In this case, what we are looking at are the options available to owners and operators of energy networks within a city, with the goal of reaching a high penetration of urban energy or distributed urban energy sources. So on the x-axis, what we see is the impact that increasing penetration will have on urban distribution grids, and then on the y-axis, the impact on the national energy system, or the eventual impact. So in early stages of penetration of these distributed supply options, as cities scale up DG, distributed generation, there is little need for expanding or reinforcing networks or for making them smarter. So in early stages, the priority is using these new technologies for better monitoring, data collection, and so on, like smart meters or other advanced metering infrastructure, to help site distributed generation where it has the least impact for the infrastructure, and to better understand patterns of energy demand within a city, where, when the demands are being generated, are being sought for. At higher penetrations, however, it becomes necessary to have smart functionalities for distributed generation. So this can include a range of technologies from automated control, how much energy is being generated by PV plants, by other distributed generators, by cogeneration. And also it could include providing grid services, power quality, or even allowing for remote control by system operators. Now, many of these options come at a very low or even negligible additional cost to suppliers. However, municipalities, city planners, and national regulators need to mandate these early on in the deployment of distributed generation, and also ensure their compliance, which is why we have here regulatory barriers that are fundamental. So as we go to even higher penetration, it becomes very important to make consumers interact more and more with how energy is produced within and beyond the city, what we call here demand-oriented distributed generation. This includes making demand more flexible, for example, through smart metering or demand response, and looking for opportunities for interaction between different sectors, so that local demand for energy can also be matched with the increasing local supply. And here we call power to X. That's power coupled to other sectors. So here what we decided in ETP 2016 to begin studying some of this potential for some of these options, we looked at one of these axes, which is power to heat. And this means coupling the production and the consumption of electricity with the production and consumption of heat. Now, most distributed low-carbon generation options and the fastest-growing renewable options like wind and solar are variable in nature. So when we look at matching the supply with demand, we look at demands that remain unutilized for a large part of the day or maybe a large part of the year, and that can therefore be shifted in large amounts. In the case of heat, we can look at the annual demand and compare it with the annual demand of electricity in what is called a low duration curve. In this case, the low duration curves, we order the hour with the highest demand first and the hour with highest demand second, up to the hour with the lowest demand in the year. What we see here is that the demand for heat, low-grade heat, which means low-temperature heating, space heating, water heating, is very much has a small number of hours where it has a high utilization during the year, and a large number of hours has low utilization, whereas the electricity demand remains pretty much with a much more constant utilization factor. The message is that there's a high flexibility potential in cities that have decarbonized, that have more electricity from heating, for integrating consumption and production between heat and electricity. On the other hand, we also want to do it cheaply. So heat storage is also quite inexpensive compared to storing electricity. So we went ahead and assessed how much demand could be made flexible in the 2DS scenario from the range of heating technologies that can be coupled with electricity. This is district heating networks with large hot water accumulators that have cogeneration plants that generate heat and electricity at the same time. Heat pumps in homes or also in district heating networks that have heat storages as well, among some other options. And what we see here is that there's very significant potential for making heat responsive to electricity demand and allowing for the integration of renewables and distributed generation. We see, in fact, in some of the regions, like for example North America or China, there's more potential there than there is storage capacity worldwide today. So yeah, also we looked here at the potential growing over time, and we see that, of course, in the fastest growing regions, China, with the demand for heat is growing fastest. Also, the potential naturally is also growing fast. And finally, so to summarize, to wrap up the chapter, we developed here 4 key takeaways for both the interface between national and local governments and how the supply of energy plays in that. The first takeaway, of course, is the national policy strategy need to foster the use of clean energy use and technologies, and that will trickle down to cities. But to maximize this potential, cities need to start mapping local energy resources to identify what are the cost-effective supply opportunities within their jurisdiction. This includes, we have seen maps of distributed generation options like PV, maps of rooftop photovoltaic potential, but also maps of highlighting potential use for waste heat options and of heat demand to be able to couple them. And of course, finally, to be able to look at the potential for energy networks that can couple, for example, the potential for heat, the demand for heating. Of course, technology doesn't exist in a vacuum, so we need new business models to sustainably manage the range of energy networks, including district heating, but also distribution of electricity. And finally, to have collaborative public and private R&D that targets clean energy technologies needed in the urban context, and there are many examples of technologies being adapted and applied to an urban context that become much more efficient and much more cost-effective in their application.
Thank you very much, Uwe, Araceli, and Luis. So we just learned that decentralized low-carbon electricity and heat generation within or close to urban areas, in case where industrial access it, and in the frame of smart urban energy networks, can indeed play an important role in meeting multiple energy sustainability goals. We are now moving to our country analysis on Mexico, which has embarked on an ambitious decarbonization path, and as you will see, the question here is what can be the role of Mexican citizens in this transition. So our next speaker, Jörg Husser, will walk us through the OECD economy that will still see a significant growth in urban population and demand. Before I pass the baton to Jörg, I would also like to acknowledge our colleague David Morgado, who supported the analysis on the Mexico chapter in his capacity of energy analyst in the Energy Efficiency in Emerging Economies program. So now going back to Jörg, he is the IEA Program Officer for Latin America. is in charge of coordinating the IEA's relations with governments and stakeholders in the region, as well as analyzing energy policy developments in key Latin American countries, particularly Mexico, Brazil, and Chile. Jörg, please.
Thank you very much, Daniele. And good afternoon, everyone. Well, on Mexico, let's first start with the status quo where Mexico stands right now and with their ambitious goal for emissions reduction. So looking at Mexico's total primary energy supply in 2013, it's obvious that this is an energy mix dominated by fossil fuels. More than 90% of total primary energy supply is fossil. And so the goal of reducing Mexico's emissions by 50% compared to 2000 levels by 2050 is effectively a thorough overhaul of the current energy system of this country. And so the contribution of cities will be crucial to achieve this goal. And in what follows, we'll look at how this could play out. Now, first, to say a few more words on the overall transition and the contribution of sectors to Mexico's overall transition according to the ETP scenarios. We see on this slide that Mexico is on track for a close to doubling of its CO2 emissions to 2050 in the 6DS. And we see that those emissions will be dominated by power sector, by the transport sector, which is a very significant contribution in the Mexican case to overall emissions in 2050. And now to see that for the emissions reductions vis-a-vis the 2DS then, on the right side, we see that power sector, transport sector, and industry are the main contributors to the overall energy transition in Mexico. So let's see now how this plays out in the urban sector, which has a specific contribution to make. First of all, we see on the left-hand side that the urban sector at the moment has already more than half of final energy demand in Mexico. And compared to the 4-degree scenario in 2050, we see the share of the urban sector increasing. And that is not only due to increased urbanization, but also to first of all, the share of urban population will grow from 73% to 83% by 2020, for example. And we see this trend continuing, a higher share of urban population, but also urban activity, urban economic activity as such will have an increasing tendency in Mexico. And with energy shifts to the urban sector. Now, moving to the urban versus non-urban energy savings in the middle, we can see that more than half of savings happen in cities, according also in line with the increased share of cities in the energy demand. And we see that more than half of the savings can happen in the urban transport and building sectors specifically. So looking at it, drilling a bit down then into these sectors, starting with the building sector, on the left hand we see how energy consumption in the building sector explodes basically from 2013 in the 6-degree scenario. And in the middle, you can see that urban energy savings in the building sector are basically building savings happen in the cities almost exclusively. And within that, what John Dulek earlier mentioned already, it's striking to see the evolution of space cooling. If you look at space cooling in 2013, comparing with the 6DS, the light green part of energy consumption raises significantly. Not least because air conditioning is at the moment still at a low penetration rate in Mexico, and we expect it to grow significantly in the next decade. So accordingly, space cooling has also the highest, or one of the highest shares in the urban savings potential in the middle. Second point on the savings then, is water heating, which we see here the dark blue area in the middle. So these two areas are two key priorities for savings in the building sector. Further savings then happen in appliances and lighting. So Mexico has some experience with using social housing programs to start deploying sustainable buildings technologies and efficient technologies in the country. These are EcoCasa and the National Appropriate Mitigation Measures, NAMAs, that Mexico has launched in this area. And so we looked a bit into the potential to focus such efforts towards the most high-impact regions. So what you see here is on the horizontal axis the share of population in these metropolitan areas without access to decent housing, and on the vertical axis the cooling degree days. And so moving to the right and top, we find those metropolitan areas that have the highest potential or the highest impact from focusing social housing on sustainable criteria. So this could be one exercise of prioritizing the focus of programs in this area. Then moving on to the transport sector, and here, as was already stressed in earlier presentation by Pierpaolo, the question of planning emerges as the central one for the participation of cities in transport sector energy savings. In Mexico specifically, we saw that there's an unusually high share of the transport sector in total energy consumption. It's actually the record share within the OECD countries. This is a legacy of low fuel costs in the past. Fuel subsidies have been phased out over the past years, but the legacy of these still exists. And also there's a very easy access to car ownership, not least through thanks to a cross-border flow of used vehicles from the US, which usually are old and inefficient and therefore contribute to a higher fuel consumption. Now, over the last, let's say, 10 years, the number of cars in Mexican metropolitan areas has doubled, and we expect the trend to continue. So this is a very important priority area for future action. And so the 2DS summarizes here the possible of avoid, shift, and improved. So reduce the demand for transport, for urban transport, by planning cities in a way that people do not have to commute large distances. This is the first point. To shift to public transport by focusing infrastructure expenditure on these public transport systems, and deployment of low carbon vehicles and electric vehicles, gas-fired vehicles, and to deploy biofuels will be the third action in terms of the low carbon fuel option under these measures. Now, this does not only save emissions, it also has the added value of combating pollution. And currently in Mexico, 72 million people live exposed to poor air quality, according to official data. And also, people will obviously spend less time in traffic, and productivity can be raised through these measures. Planning in Mexico has already taken this as a priority area. It's mentioned in the National Development Plan in Mexico as a top priority to improve the sustainable transport systems. And indeed, the concept of compact cities has been taken up as Mexico implements urban containment perimeters around metropolitan areas to put an end to a legacy also of intense sprawl, which has led to very high numbers of kilometers traveled per person in Mexico. A second system which is already being deployed in Mexico on a larger scale is the bus rapid transit systems, and this is also something that can be deployed in the context of sustainable transport sector for Mexico. Now, as Uwe just mentioned, there is the potential also on the supply side to have cities contribute to power generation. And in this area, the potential for rooftop PV in Mexico is estimated between 949 kilowatt hours per capita and year in Cancun, and the highest number, 2,119 kilowatt hours per capita and year in Los Mochis. So these are numbers that lead to an overall power generation potential in Mexico, which would be around a third of gross power generation under the 2DS by 2050. Now, in the past, it was very hard to tap this potential under the monopoly setup of the power sector. But energy reforms recently have opened the door to using greater share of rooftop PV in Mexico. And recent auction results have also shown that solar can be competitive and even more cheaper. I mean, in the utility scale, PV can be cheaper than natural gas. Moving to waste to energy, waste generation in Mexican cities is still below the OECD average, and so has some growth potential, not only through higher collection rates, but also due to the higher urban population that we expect in the future. So by 2050, technically, waste to energy could cover 15% of residential power supply. Now here, again, there is an issue with implementing waste to energy due to municipal responsibilities, while federal level also has standards to set. So to navigate such complex landscape could be a potential for energy service companies to start up this potential. On cogeneration, there is a large potential as well, often located close to large cities. Alone in the national oil company Pemex, 5 out of 7 gigawatts of cogeneration that are planned to be deployed over the next by 2020, 5 out of 7 gigawatts come from the national oil company Pemex. So one can expect that there is more to come in this area. Finally, on smart grids, and Luis has just mentioned it, that smart grids are the key enabling factor that is also to deploy renewables in cities, and cities can actually be the laboratory then for a larger scale deployment along the country. So they balance demand and supply and can regulate the storage options. And a specific point in Mexico is additionally their contribution to loss reduction, which is a large issue in Mexico. Now, to sum it up and mention a few elements of a strategy to make the urban sustainable energy transition happen, is the first key point multi-level governance. This is as much horizontal coordination as vertical, meaning horizontal coordination between different secretariats of government to integrate different sectoral policies, energy, transport, environmental policies across the federal government, but then again, especially vertically, deploying all these priorities and policies at state and municipal level are crucial, and for many issues such as just mentioned waste to energy, but an even more important point here is building code enforcement, where federal government can set standards, but by constitution implementation is left to municipalities, which often lack the human resources or capacities to actually enforce these standards. In terms of planning, the deployment of an integrated planning, also transport planning within that, along the lines of a compact city concept, will be crucial to overcome the legacy of sprawl that has happened in Mexico since the 80s and also in the 90s still, and reduce the number of kilometers that people travel just to get from home to work and back. and as indicated, it has multiple benefits that go beyond the CO2 emission mitigation. A deliberate push for public transport is needed, and many priorities in public infrastructure funds are still dominated by a car-centered vision. So this has to be overcome over time to reach the 2-degree scenario. To deploy a low-carbon power generation in cities, smart grids will have to be deployed to enable the deployment. And finally, public housing programs should actually be used and scaled up to set sustainable examples for the rest of the country. With these elements of the strategy, I give back to Daniele. Thank you.
Thank you very much, Jörg. So we have learned that Mexican cities have all the potential to be strategic enablers of the Mexican low-carbon transition, and Mexico is already showing to the world that it is indeed possible to achieve vertical integration and to coordinate among different levels of governance, so that with the right commitments of national and subnational governments, then eventually Mexican cities can, cities overall can drive decarbonization. So, and we will now move to our next presentation, which is dealing about policy and finance mechanisms for urban areas. So going back to the global analysis, we know now that urban energy systems are at the heart of the global energy transition, in that they offer vast potential to deploy low-carbon energy solutions. But so far so good in terms of potential. But how do we get there? We already had some insights through the different sectorial presentations, but in the next presentation I will describe the policy and finance mechanisms that can mobilize this sustainable urban energy potential into a more systems perspective. So as for myself, in parallel with my project management role, I also enjoyed participating in the analysis and also drafting different sections of the report, including one section in this chapter which had as main author Tyler Bryant, which unfortunately today cannot be presenting, so I will do it on his behalf. So moving to the broader, I would say, energy systems dynamics, the interaction between the national and local levels can be best understood, obviously, from a systems perspective, and urban sustainable energy transitions can be thought as embed into the broader context of national transitions, though obviously national dynamics in reality are greatly shaped by what is happening within cities. In fact, cities themselves can be test beds or drivers of wider social, economic, and technological innovation, as we have seen with their home of more than half of the global population and generate more than 80% of the GDP. So the transition to sustainable urban energy systems needs to involve all actors that make up the urban energy nexus. These actors include the higher levels of government, developers, commercial enterprises, utilities, not only the local one obviously, but also the regional and national ones, energy services companies, community organizations, other NGOs and consultancies, and other institutions such as, for instance, health and educational authorities. So all municipal authorities or local energy planners with basic planning powers can improve the energy efficiency of their urban system, and they can also support the uptake of local low carbon generation. So what you see here, essentially the wide range of sustainable energy policies and strategies that can be pursued by cities, and this will obviously depend on their powers and their governance models. As cities move up the scale of action and achieve more of the sustainable energy potential in urban areas, then the number of possible strategies, policies, and other actions will expand. But this actually will bring governance challenges, as there will be an increased need for greater intergovernmental coordination and also shared responsibility between the key actors. So how do we for the transition? Making the transition to sustainable energy systems requires investment, but there are financial mechanisms to raise these resources. Most cities, though, have a narrow tax basis and limited powers to raise revenues. So in this case, new financing and business models can fill the gap. And in those cases where the amount of funding is actually beyond the means of most public sources, then private financing and commercial business will need to be leveraged. But then again, public policy that can strengthen the market for low carbon investments can serve the purpose of leveraging to the private sector, and the private sector itself seeks undertake innovative approaches to develop and finance projects. So as the ambition to achieve greater urban energy sustainability grows, then leveraged private lending and business models will have a greater role. So to conclude this section, local and national policy makers need to increase their efforts to ensure that the right conditions are in place in order to enable cities fulfilling this low carbon potential that we have seen so far. And local policymakers have different options available, as we have already seen in the previous slide. The list that you see here is by no means exhaustive, but what we recommend as the IEA is the fast uptake of sustainable energy planning, with many success stories around in the world, and a sustainable energy planning that can holistically include various pieces of this mosaic, and such as integrated land use and transport planning, sustainable energy utilities, and others. However, local policymakers need to be supported by national governments in unlocking these urban sustainable energy potential. And this can happen basically through a combination of enabling frameworks and regulatory approaches on the part of the same national governments. So capacity building and financial assistance are crucial for cities in emerging economies, and in these cities, as we've seen previously, there are many opportunities for securing so-called low-carbon lock-in of the overall energy infrastructure that would avoid essentially the same carbon-intensive paths of many of the cities in developed economies. So in conclusion, there is no single template, and policymakers need to choose the appropriate mix of strategies and solutions according to the specifics of cities and countries. So this concludes essentially the series of presentation. I would like just to highlight a few broad conclusions here that overall COP21 can be a turning point in terms of accelerating low carbon deployment, and it can do so also through by catalyzing more innovation and research investment in clean energy technologies. And in 2015, we saw basically strong progress in a few clean energy technologies like solar PV, wind, and electric vehicles, but other areas such as CCS and biofuels are lagging behind with respect to the intermediate targets of our 2-degree scenario by 2025. And now going back to cities, cities in emerging and developing economies can lead the low carbon transition while reaping many benefits. So it's not only about making climate change mitigation happen, this is about energy access, energy affordability, reduced air pollution, and increased resilience as well. So in urban system, we've seen that efficient heating and cooling system, better public transport, and low carbon vehicles are essentially critical pillars to decarbonize cities. And overall, national and local governments need to work together, but also they have to act together with industry, and through international cooperation can greatly accelerate technology innovation, which can in turn make the transition to a 2-degree scenario more feasible and faster. So right now we'll just go through a few Q&As with my colleagues, and I've tried to condense some of the questions that we received in the online Q&A platform in basically broader questions to my colleagues. And I'd like to start with Eric Massonet on the Eric, can you comment on some of the difficulties that in analyzing urban energy use, and can you do you have any recommendation for improving such analysis in the future? Because I've seen you going through the overall urban energy demand analysis and further than that.
Thanks, Daniele. It's a really good question. First off, yes, it is quite difficult to estimate the energy use of urban areas at a global scale, and the primary reason for that is lack of data. And as a result, there have been very few estimates that have appeared to date in the literature. One of the main reasons for lack of data is that while many countries have very detailed statistics on population, economic activity, housing characteristics, not every country will report that at the urban scale. And those that do will often have different definitions of what constitutes. It's a density threshold, meaning so many persons per square kilometer would qualify as an urban area, but even those definitions differ between countries and between cities. So there really is no universal definition of what is an urban area that can be used in an analysis, and the data for populating the analysis are often lacking for many countries. Similarly, another major data gap is that of energy data. So while most countries collect and report energy data at the national level, most often those data aren't reported at the urban scale, which means that in looking at a global analysis of urban energy use, one needs to make a lot of assumptions. And in ETP 2016, we have a method that we've applied based on population and GDP and some other factors that are all detailed in the book. But there really is a need for better urban scale data. Interestingly, over the course of the last year, as we were researching and writing this book, there's been quite some development in providing these data, both from government and non-government sources. So, for example, in the UK, the Department of Energy and Climate Change is reporting now subnational energy consumption statistics, which partially fill some of these data gaps. And there are organizations like CDP and the World Council on City Data, which are beginning to report urban scale data. So slowly we're filling those data gaps. But in the book, we strongly recommend that national and local governments invest much more heavily in the data aspects, meaning defining consistent standards for urban scale data reporting, and then actually going out and gathering and reporting those data on a regular basis in order to accelerate data availability, not only to the research community and institutions like the IEA, which will use them for analysis, but also for the countries and the cities themselves. And we further recommend in the book that cities use those data and they invest in models and analysis tools that allow them to understand where energy use is and where it's going. As I described in the presentation for Chapter 3, urban areas and cities are very complex systems, and identifying the best technologies requires understanding of supply and demand side options, how behavioral trends and urban form affect the system, and many other variables. So it's not a straightforward task. In the book, we document a few case studies of institutions that are using energy models in order to inform energy plans in the UK and in Switzerland, for example. But there's a lot of investment and progress that needs to be made so that cities can first gather the data and then use them to make the most informed decisions moving forward.
Great. Thank you, Eric. And we will obviously continue to our work on urban energy systems, and we will look forward to improving our modeling capabilities in this area. I have two questions for John on buildings, and there is quite a lively narrative on the rebound effect. Don't you think that tighter building codes, building envelopes in developing countries would lead to actually ending up leading to a greater cooling demand?
Thanks, Daniele. This is a good question. We've seen examples already in many hot climates, both in developed and developed countries, where as we've increased particularly air sealing and insulation in buildings, the tightness of the building, that the internal loads, both from human presence and from equipment, have increased the demand for cooling within the building. Within this respect, it's very important to design both building codes at a local and regional level, as well as building design to accommodate both the external heat gain as well as the internal heat gains within a building, to ensure that we are reducing as much as possible the need for mechanical cooling within a building. Now, this obviously can be done through several ways. We know of many traditional building construction techniques that, for example, take advantage of natural shading, or for example, the orientation of the building relative to a sun to address the amount of heat gain within the building, and at the same time also take advantage of natural cooling opportunities, whether that be through natural ventilation or, for example, through the right design of the flow of air through a building, for example. These are all very difficult to answer, of course, at a global scale. It is very much a local building design and building code issue, but we should be ensuring that we are taking this into account when designing sustainable buildings for the future, especially as the current trends, which typically have large amounts of glass, especially in commercial buildings, and that also are not necessarily taking care of ventilation properly in buildings, are increasing the demand for both heating and cooling loads in buildings across the globe.
Okay, thank you, John. I actually have another question for you. And since we see by pushing for energy efficiency and reducing heating loads in buildings in area where there is a strong heat demand, basically how would this impact the economic viability of district heating networks?
Okay, another very good question. Something that particularly here in Europe is at the forefront of the discussions on the heating and cooling strategies for the EU, but that also, of course, is an issue in other areas with large district heat networks like China and Russia and some parts of North America. In thinking about building design, we first and foremost should take into account that the movement of the global building stock, particularly with regards to renovations, is currently at a very slow pace. And even in the 2DS scenario, we would still be looking at rates of 1 to 3% of buildings being renovated per year. So first and foremost, this means that we have time to strategically plan these decisions, and that the reductions in heating demand for buildings that are currently connected to district heat networks would not happen overnight. And again, this comes back to the previous point that we need to think about designing both the energy efficiency measures in buildings as well as with the decarbonization of heat production for district heat simultaneously, so that we are taking this into account at the local planning level. The second is that we have traditionally seen from a district heating perspective the business perspective of only considering buildings as a consumer. In other words, that the commercial purpose has been selling heat. And increasingly what we are seeing in some of the very innovative business structures are actually seeing heat as a service provision to buildings, where in some communities district heat providers are actually becoming energy service providers and are working with building association and building owners to actually plan the strategic process of building renovation in line with their district heating improvement measures, so that they know when the energy efficiency measures will be made and they can take into account the right business decisions that will continue to maintain the economic viability of those district heat networks. So I think as a broad conclusion here, the movement of this market is not going to happen overnight. We need to be much more aggressive, certainly to think about how these decisions are made across the district energy networks within cities.
Thank you very much, John. We will end for the time being. So, and we will move now to transport with Pierpaolo. Pierpaolo, do you think that there can be policies that can give win-win solutions in terms of the impact to basically reduce the amount of travel and at the same time have vehicle efficiency improvements, because we know that there are a lot of trade-offs there that not necessarily are always positive.
Thanks, Daniele. I think there are actually all the policies that have something to do with have an impact on cost of driving tend to lead to mitigation of kilometers driven and an improvement of the average cost of the average consumption per kilometer. So, for instance, policies that would such as CO2 taxes on fossil fuels, or even differentiated taxation that is based on energy efficiency performances of vehicles, will end up increasing costs for car that consume more and would result in an incentive to actually travel less. As far as the differentiated taxation, there could be some reverse impact, actually due to rebound, because you have more efficient cars, you may have an incentive to travel a little bit more, but overall, I would say a combination of policy instruments that makes sure that the average cost of driving doesn't fall radically are good solutions here. Also on the local side, there are policies that would lead there. So we talked about compact cities policies which would reduce the distances, so this is not necessarily something that would impact directly the vehicle technologies, but in perspective, if you have lower distances to be covered by individuals within cities, you are favoring technologies that struggle a little bit more to deliver good performances with respect to range. So that, for instance, could be the short distance trips are well coupled with the uptake of electrification in urban areas. So to some extent, local measures can also provide win-win solutions to reduce the total activity and enhance the energy efficiency.
Thank you very much, Pierpaolo. Now, moving to the to complete the series of end-use sectors to industry, it was actually surprising to know that during the analysis that the industry's excess heat that could be recovered is equivalent to 2% of the industry final energy demand, and of course in percentage terms might not seem that significant, but if you look at the actual exajoules or MTOE, it is quite significant. I have one question for Araceli. So what do you think would be the next steps needed to analyze the cost-effective potential of industrial heat in a specific area?
Thanks, Daniele. I to take an energy efficiency approach as described in the presentation. The first approach for this will be really to understand at which extent, from a cost competitive perspective, the generation of industrial excess heat can be avoided in the first place in different industrial processes. So in this case, really policies that would support energy efficiency measures, energy management systems that would also support the integration or the application of process integration techniques would help really to monitor and identify cost-effective opportunities at the site level to really reduce the consumption of input energy in the first place. On a second approach, on a second step, analytically, the idea would be really to perform exercises in the form of thermal maps, so thermal mappings, where we could really understand in a specific area or region where are the different thermal providers, let's say thermal energy providers or excess energy providers, and the different thermal needs. Also comparing the different temperature levels, so at which extent these sinks and sources for energy are compatible. And of course, this will already give us an idea of where the greatest priorities in terms of opportunities from a cost perspective could be, considering also the type of infrastructure that's already built in place. So yeah, I mean, in that case, the other aspect also to consider is that, of course, areas which would include, let's say, densified industrial production sites, industrial clusters will be more optimal for this type of approaches, where if it's a case where there's no existing infrastructure, we're looking at reaching different industrial sites with compatible uses and demands. That would be interesting from a first perspective just to look at. But the idea is as I mentioned, really to build on this energy efficiency perspective and try to drill down from this prioritization those opportunities technologies. Also, of course, from a cost-competitive approach, the idea would be to start with commercially available recovery technologies that could offer a more, let's say, competitive investment cost to start with. And of course, if we start by medium and high temperature excess heat sources, that will also give us a greater food for thought in the sense that the size of the equipment that would be required from a recovery perspective will be more limited. So we will be looking at most beneficial, let's say, impact to start with. And then if we go down in that path, then we will start looking at low temperature excess heat sources where it will be more difficult to, let's say, recover from an economic perspective, but there will still maybe very good gains if depending on the local conditions. So it's just a matter of really following that methodology from an energy efficiency prioritization perspective.
Thank you very much, Araceli. And so now moving back to the country perspective with Mexico. So we know that there is an ongoing energy reform in Mexico, and could you elaborate a little bit how this energy reform would impact on the ability to reach the 2-degree scenario in Mexico over the long term?
Yes, thank you very much, Daniele. On this, basically the Mexican energy reform is mostly perceived through the lens of oil production and an attempt to raise oil production in Mexico. But in reality, and as important in this reform is the reform of the power sector, where Mexico moves away from the monopoly market it had dominated by the public utility CFE to a competitive market. And this shift basically allows two important developments that have an impact on the 2-degree scenario attainment, which is that through the reform, much more investment is going into bringing natural gas into Mexico to replace fuel oil, which was until recently still used in a quite significant way in Mexico to generate electricity. So this shift from fuel oil to gas is accelerated by the reform and enabled really to happen. So billions of dollars have to be invested in the pipelines and infrastructure to do this. So this is one important point. And another shift is the longer-term shift into renewables. For the first time, Mexico has held weeks ago, a long-term auction of renewables, and it showed that solar energy was competitive with natural gas-fired power generation. At $42 per megawatt hour, one of the lowest prices reached globally. So this showed for the first time to everyone that actually solar PV at a utility scale is already now competitive in Mexico, which under the previous market setup was never considered a possibility. So everyone was, at least in Mexico, was surprised. Many observers outside of Mexico had already earlier pointed to this large potential, but now it's obvious to everyone, and this is an effect of the new setup, the new market setup, which allows these long-term auctions to happen and which also foresees clean energy certificates to be assigned to the power generation that comes from these projects. So there are instruments, market-based instruments foreseen under this reform that will help enable the big shift that we foresee in the 2-degree scenario for Mexico. So I think these big shifts are the two things that are enabled by the reform.
Thank you, Jörg. So we have received quite a few questions, and we apologize in advance if we were not able to address all of them. And for the time being, what I would like to mention is that as a ETP team, we are looking into carrying out a preliminary analysis on the well below 2-degree scenario. And with that comes one of the questions from the audience. The question is from our colleague Rodrigo Villarroel-Walker from WRI, which, by the way, I'll take the opportunity to acknowledge WRI as one of our strategic partners in the ETP 2016 analysis. I would have done that at the end, but since you're still with us, Rodrigo, I'll do that right now. So the question is, moving forward toward the 2-degree target, and even more so with the 1.5 2-degree scenario, requires aggressive implementation of policies at the national and local level. How do you think these national and local policies can be coordinated in practice so that they support each other? I like to ask this question to some of our sector leads, because I think we first have to approach this from a more granular perspective within each sector, and then I'll try to take a stab at a more systems perspective. So I'll first ask John whether he can comment on that.
Sure. Thanks, Daniele, and thanks, Rodrigo. I think looking at the building sector, there's obviously a significant potential for energy efficiency improvements that would be support in both the 2DS and looking beyond that, a well below 2DS scenario. As I mentioned, most of the technologies that we would expect in a 2-degree scenario for the building sector are on the market today. It's really an issue of deployment and market conditioning, as well as providing the right policy tools and financial incentives to actually get the market moving in that direction. So in that sense, looking at the bridge between national and local policymakers, I think many of the points raised, particularly in the policy presentation and the presentation by my colleague Eric at the beginning of today's webinar, looking at how to bridge this gap, are particularly important in the building sector. This would be, for example, looking at different national policy levers that would support, for example, local energy authorities and stakeholders in the renovation of buildings, or education and training of local authorities to enforce building energy codes for new construction, as well as putting the right incentives on the table to get the private sector to start to pick up these technologies, in pair, of course, with energy performance standards that could be augmented by local policymakers. As maybe a specific example of this, something we've seen in this field in the last couple of years is quite promising, and that really demonstrates the interaction of different actors, would be a project in the Netherlands called Energiesprong, where essentially across building housing associations, the national government, who is providing low-interest bonds for housing renovations in the Netherlands, building constructors, and local communities, the consortium of all these actors have put together a program that has ramped up renovation of existing housing stock to date, roughly 100,000 buildings, where the combination of the different policy tools and the incentives provided by the national government through the low-interest bond process, as well as the bringing together of the right stakeholders, including the housing associations and building constructors, to provide cost-effective measures to really drastically reduce energy demand for space heating in buildings, has been very successful. And we would like to see more of these types of programs and initiatives to really raise awareness and the feasibility of these types of deep energy retrofits in buildings, as we would do the same, for example, in bringing the right tools and incentives to urban areas to drive highly efficient new building construction.
Thank you, John. I'd like to call in now the transport sector. So I'll just repeat the question. So moving forward toward the 2-degree target, 2-degree scenario target, and even farther below, will require an aggressive implementation of policies both at the national and local level. So do you think that in the case of transport, these policies can be coordinated? Can policies essentially get us there, Pierpaolo, for the transport sector?
Thanks, Daniel. Yeah, I think that the absence of policies was there for sure. So definitely need policies to move towards the 2 degree below. I think the exercise we made for ATP 2016 shows that if we align well national and local instruments, we can actually get a long way from where we are and where we would go in the absence of policies, and that there is a significant challenge in terms of making sure that the national framework and the local actions are well coordinated. I would say ETP 2016 also, given that it had a specific focus on urban areas, delivered messages that were more relevant for passenger mobility than for freight. My personal understanding is that in order to move actually below the 2 degree target, tackling exclusively or only or primarily, let's say, passenger mobility will not be enough. And so policies will have to move beyond that. Even though we do have actions, for instance, in terms of improved energy efficiency in road freight, and also modal shift already in the ETP 2016 scenario, I think that if we had to look at stronger reductions, we will have to think about or look more deeply into technologies and policies that would actually bring CO2 emission savings for freight transportation, which today accounts for about a third of the road transport energy use, and so also CO2 emissions.
Thank you very much, Pierpaolo. And now I'd be curious to know about the industry sector on whether there is any role from local policies on achieving a low carbon industry sector, and on whether what in general how national and local could interface with each other for industry.
Thanks, Daniele. I mean, certainly, if we look at that 2 degrees CO2 trajectory, and even a more ambitious below 2 degrees trajectory, I mean, from an industry perspective, we need to really make the most of any possible lever to reduce the CO2 footprint of industry activity. So, I mean, it's not just only about maximizing energy efficiency, looking at, let's say, secondary routes, looking at low carbon innovative processes. It's also about kind of really to reach that additional emission reductions area is really about breaking the sectorial boundary. And we're looking here at exploiting the most possible from local energy sources, in considering even industrial byproducts, also making the most of optimizing industrial sites, looking at their neighboring environment, if it's other industrial sites, if it's also urban areas. So definitely I think there is a room for local action to be influencing and helping industry to make their contribution into this emission reduction ambition. So we could think about opportunities for facilitating industrial clustering, as we mentioned before, that it could be beneficial to find or to reduce the, let's say, cost burden of certain infrastructure developments, but also to help also having a perspective of process integration from a more cluster perspective rather than just purely site-specific perspective, and also in terms of, for instance, facilitating the demonstration of business models that would really enable this type of exploitation of additional local energy sources, if we talk about industrial byproducts, and not just really more material or fuel byproducts, but also energy ones, as we've discussed the role of excess heat. So definitely there's potential for that type of interaction, and it would develop. It will become more important in a below 2 degrees than in a 2 degrees.
Thank you, Araceli. And now moving to power, Luis.
Thanks, Daniel. So moving forward, one of coordination is, of course, the changing role of traditional owners and operators of power systems. So the way that most electricity systems have been built up to date is to produce power in large quantities in a centralized manner and to deliver it to transmission grids, and then power flows down from transmission to distribution and then to the end consumer. With more and more distributed generation and a lot of the options that we talk about in ETP 2016, that means there's a lot more energy being produced locally. And we're already seeing that in many countries, in local distribution grids, power, instead of going in only one direction, is now starting to go back up in periods where the demand is lower than the generation in the local grid. So this means that, of course, there's a technological change there because the systems have been designed to produce and generate power in one direction. But it also means an institutional change because traditionally, for example, those in charge of ensuring that the quality of the power and the security of the supply and the reliability of the supply meets the right criteria, those have been transmission system operators. And now with more distributed energy happening in distribution grid, it means that some of these powers will need to be rethought, and some of these capacities need to be given also to the local owners and the operators. So we're seeing in many countries that already distribution operators are gaining the capacity to do their own local forecasting, to be able to know how much PV for the next few hours. The same for wind power within their area of operation. And we're also seeing that they have more and more capacity to provide reliability and to regulate that much more. The other aspect I would maybe highlight of local national coordination is much better planning, because of course with more renewables the resource is not the same everywhere, and one needs to coordinate much better how networks are planned and how the generation itself is built out. And maybe the final aspect I would mention, one key change we're seeing in power systems everywhere is more and more IT, more smartness, and that means a lot more data. And with that comes a lot of cybersecurity risks. So, and cybersecurity is an issue that's very systemic, and it requires end-to-end security. So from the end consumer to the generator, grids, and so on. And every stakeholder, every user of electricity systems has very different security requirements, and they are also operating with infrastructure that's very old. And this means that there needs to be a lot of coordination between all the different stakeholders to have a secure delivery of electricity in the future.
Thank you, Luis. I'd like now to go back to actual question that will bring the regional variability back into the picture. So the question is, what is a bigger challenge to develop urban sustainability in cold climates, such as the Siberian region, or in hot climates? Is climate a challenge at all? So John, could you elaborate a bit on that?
Thanks, Daniele. This is a good question. I wouldn't define necessarily as which region would be more challenging, but what are the different opportunities relative to the regional challenges. If we're looking, for example, at urban areas in both regions, the large part of which are already established in most of the Northern Hemisphere, then again, we're really looking at changing the way we've done business for the last century. For example, building stock at drastically improving the thermal intensity of buildings, whether this be through building energy efficiency measures, changing inefficient equipment for more efficient heating, for example, or through building integration with low-carbon, energy-efficient district heating networks, which of course could take advantage of multiple sources, whether they be renewables or excess heat from industry or even using, for example, geothermal sources or capturing heat and cooling, for that matter, from sources like rivers and lakes. Whereas obviously in many hot climates, particularly in the developing world, the challenge and opportunities moving forward are really those of new construction, where integration of the most efficient equipment really could prevent lock-in of inefficient assets for quite a long time to come. And this would also support multiple socioeconomic goals, for example, job creation by moving people to the right industries and getting out energy-efficient technologies for the markets. Also, when looking at energy access, which is still, for many parts of the developing world, a critical socioeconomic priority for governments, where we know, for example, that peak electricity demand for things like cooling in hot climates can actually lead to brownouts and blackouts. And energy efficiency, of course, would help to reduce those peak demands, and while at the same time also allowing further additions in terms of electrification of households to the grid. And so in that sense, it's really defining the way those hot climates want to develop to ensure that they are low carbon and sustainable in support of their broader economic development goals, whereas perhaps the challenges for much of the developing world in colder climates is really changing the way we have done things for quite a long time.
Thank you, John. And we've just received a question on Mexico. So the question is, regarding Mexico City, what are the critical issues the IEA considers necessary to solve the environmental and mobility problems we are facing? So I suppose our friend is from Mexico City. Jörg, would you like to address this question?
Yes, thanks a lot for the question. Well, let's see. So environmental and mobility challenges, there are several things involved here that we need to separate. So I guess firstly, on the environmental side, you're alluding to the recent activation, or several activations of the contingency mechanism that Mexico City has to cope with the bad air quality that has emerged due to local climate conditions several times over the past months. And well, on this one, a key point is to actually enforce forcefully the existing vehicle certification standards that exist to move towards better air quality and to avoid contingency situations to emerge. On the mobility side, there are several strategies and along the lines of avoid, shift, and improve that one can mention. And I would especially highlight, for example, obviously, as mentioned, as one of the strategies to actually scale up public transport, expand the existing public transport systems that Mexico City has, but then to extend that also through campaigns to change behaviors, for example, carpooling, a campaign to promote carpooling. People that come from the same area of town can share their car to go to work instead of one person sitting in each of the cars that are congesting the streets. Park and ride schemes to have parking lots around the endpoints of the BRT systems so that people can drive to those endpoints, leave the car for the day, and commute for the rest of the factory by public transport. So these kinds of things to enable people to actually use the public transport system. So these are a few ideas that I would offer, but maybe I can also invite Paulo to add a few more options along the lines of improving public transport in Mexico City, avoid, shift, improve.
Yeah, I think you mentioned earlier the fact that Mexico is transitioning out from a situation where fuels have been subsidized and which leads to a legacy of relatively inefficient and system, which leads to a legacy of, which is represented by a relatively inefficient system with respect to energy per unit passenger kilometer or ton kilometer. So broadly speaking, Mexico City is in that framework, and so there are issues with respect to the energy intensity of the vehicles, but also, as you say, in terms of how the city itself is structured. So relatively long distances from point A to point B, which have been incentivized by the fact that you don't need to pay so much to actually move from point A to point B. That also has drawbacks which are measurable in terms of, for instance, congestion levels and local pollution. So the transition towards a more sustainable future goes through the deployment, the additional deployment of collective transportation, and so that could take the form of BRT. BRT has been interesting in Mexico as well as in other Latin American cities because of the relatively low cost per capacity of people transported, and so as a mean to actually accommodate significant amounts of mobility with small investments. I think in perspective, and also thinking about a situation where Mexico will become a richer country, and Mexico City as well, developments that build on the initial BRT deployment and increase BRT deployment, and also combine with other high-capacity public transportation infrastructure. So, for instance, strengthening the rail urban network will also be consistent with the recommendations we're talking about. And ways to finance that include leveraging the fact that mobility taking place on personal vehicles, on cars, is leading to this type of externalities such as congestion of local pollution. And so there's a good rationale to actually penalize polluters in order to favor the deployment of more sustainable public transport infrastructure.
Yeah, thanks a lot, Paulo. Maybe just to add, because underline what you said on the re-densification. I mean, to overcome this legacy of sprawl that Mexico City has, there must be a deliberate policy put in place that tries to re-densify areas where the sprawl is specifically intense, and to try and get workplaces close to where people live through planning, but also through campaigns in cooperation with industry, maybe. So there can be several things can be done to try and re-densify cities beyond the already existing instrument of the metropolitan containment parameters, which have been defined and would already try to incentivize developments in the spaces in between, so to speak, where there's empty land far away from cities. So these are a few more, and then obviously to make car use less attractive has to go in line with fostering the public transport. So one can, for example, reduce the number of parking spaces in center city areas, so that it's simply not as attractive anymore to go there. Paris, for example, has eliminated whole lanes from main avenues or main corridors through the city to make it less attractive to go to the city center, and maybe we'll shift to other transport modes. So these are another few options. With that, I would then hand it back to Daniel. Thanks.
Thank you, Jörg. I would now like to have a question on urban energy supply, and particularly on rooftop solar PV. So the question is, can you suggest methods to estimate rooftop potential of, I suppose, rooftop PV potential of a given geographic area from Tushar? Uwe?
Yeah, thanks for the question. I mean, as I already mentioned during the presentation on energy supply in cities, what we did on rooftop PV is kind of simplified to aggregated approach to estimate which roof area is available in cities. It's really concrete cities in mind, and that has been in the past, like the solar maps and solar assessments. One can really identify the three-dimensional structure of the building, count shading effects from neighboring buildings to really identify what the actual potential that could be used for either rooftop PV, and always keeping in mind all the competition with solar thermal water heating. So in that sense, there are already quite some good tools, methodology available. Often the challenges for cities, especially for smaller cities, they don't have the resources to provide these kind of assessments. So their regional or even national governments could step in to help to provide that these assessments can be done for the smaller cities. And if we talk about resources and potentials, I would also like to stress, because we haven't really talked much about it during the presentation, that one should not neglect the potentials outside of cities, which are close to cities, meaning that these potentials, for example, we talk about wind farms. For example, Copenhagen is investing into offshore wind farms outside the cities, but it's something that has very low transmission costs close to the consumers. So one should not neglect looking at opportunities outside of cities. So it doesn't necessarily mean that something, because it's in the city, it's always cheap and cost effective. One really has to look at the resource conditions and look at the trade-off between using resources and importing electricity from outside cities. In that respect, we are currently still finalizing some analysis, looking at the renewable potentials in the region, taking into account only issues or factors like capacity, factors that also look at the distance of these renewable potentials to cities, to the load centers, and also differentiating by city size. So in that sense, we'll clearly have a better handle on the cost of using different renewable resources depending on what is the quality in terms of capacity factors, where they're located, where the demand located. So trying to take into account these costs when deciding which resources to use depending on the electricity demand, for example.
Thank you very much, Uwe. I think that the time for conclusions has come. And before doing that, I would like to acknowledge all organizations that are playing a leading role in fostering urban energy sustainability and low carbon cities, which have also provided valuable feedback to improve our analysis. So first of all, the World Resources Institute, with which we enjoyed an analytical partnership, and our colleagues Rodrigo Villaroy-Walker and Benoit Lefebvre provided, along with their colleagues, obviously, case studies and suggestions. And then the Stockholm Environment Institute with Pete Eriksson and Jeff Brooke, interesting conversations. And then on the, I would say, more institutional, operational side, we have been in touch with C40, ECLI, the Compact of Mayors, as well as the Covenant of Mayors. We are grateful to all reviewers, the more than 200 reviewers that provided their inputs into improving our analysis. And then our colleagues at the IEA and the World Energy Outlook team, which made the urban GDP analysis possible, providing their results from their GDP projections. And so thank you very much for being with us today. PDF version of the presentation, along with the recording of the webinar, will be posted on the ETP website next week. We encourage you to look at our online database and to provide comments and feedback to our work. And if you wish to be included in our contact list for the next webinars, please send us your coordinates at the email that you see at the bottom of this slide, and we'll make sure that we will keep you in the loop. So finally, I'd like to thank my colleagues within the ETP team. It was a great learning experience for me, being here for the last 2 years. My division head, Jean-Francois Gagné, the director of the Sustainability and Technology Outlooks Directorate, Kamel Ben-Nasser, our director, Fatih Birol. Thank you very much, and hope to see you soon, although virtually, in one of our next events. Goodbye.